Hello, am I audible?
Yes, sir.
Okay. So yeah, so basically, I want to revise a few concepts from week 1 and 2. So basically, I just want to know, so what are the topics that you want me to cover from week 1 and 2 uh, in this session?
I am having a bit of problem with the functions. Can you explain a bit functions and give an example of them, like as we have done in the example?
Okay, okay, fine, fine.
So I also have a problem with relations in week one.
Yeah.
I'm a non-math student.
Okay, noted. Yeah. Okay, so okay, I'll start now then.
So I have problem in types of functions.
Yeah, got it, got it. So basically, so it's more about, so what basically I observed is more about relation, types of relation, and you have function and as well as types of functions. Okay.
Uh, if you can also explain straight line bit as well with that.
Yes, sir. I'm expecting an outline of week 2 conductors.
Okay, fine. Okay, I'll try to, so certainly there is one more session on week 1 as well. Okay, it's certainly it's a doubt clearing session, but if there are few things that I can't cover in this session, then certainly I will tell the next person to revise the concept as well. Okay. Okay, so let me start and I'll try to go slow. Okay. Okay, so yeah, please mute yourself, and if you have question, then only you ask. Okay, so don't unmute yourself if you don't have any question, because I'm getting a lot of noises. Okay, it's better if you mute yourself, and whenever you have doubt at that time, you unmute yourself and ask your question. Okay. Okay, fine. Okay, so before going into relation, so the first thing that you should know is basically Cartesian product, because by using Cartesian product only you define relation. Okay, so suppose you have two sets. Okay, so you have suppose two sets A and B. Let's say you have two set A and B. How you define the Cartesian product of A and B? What is the Cartesian product of A and B? Anyone?
Number of elements of A and number of elements of B.
No, that is incorrect.
All the possible pairs of elements of A and elements of B.
So okay, again, like not all the possible pair, because basically the first component of that pair is should be a member of this set A, and the second
one should be from B.
B should come from this set B. Okay, so the Cartesian product is defined like this. Okay, so this is all the possible pairs A comma B, right? All the possible pair A comma B such that the first component should come from A, right? And the second component should come from B, right? So, sorry? Okay, so basically what is Cartesian product of A and B? So that is basically, so the Cartesian product, we denote this Cartesian product as A times B. Okay, this is basically the notation for Cartesian product of A and B. So the Cartesian product of A times B, which is basically defined as all the possible tuples A comma B, where the first element of this tuple, that is A, the first element of this tuple, okay, so that is precisely A, should come from this set A, okay, and the second element of this tuple, okay, that is B, should come from the set B. Okay, so this is how we define the Cartesian product. For example, let's say take A to be 1 2 and my set B to be, let's say, math, let's say this is, let's say, M, okay, and M basically denotes math, and S denotes stat, C denotes basically computational thinking. It's okay, these are the elements of set B. Okay, so then how actually so then what will be the set A times B? It's basically all the possible pairs A comma B, where A comes from A and B, the small b, comes from
Total
this.
number of six
Sir,
pair.
here number of 2
Six
into 3,
pair
6.
total number of pair.
No, I'm not
7.
asking. I'm not asking about the cardinality. I'm asking about the set. Okay, don't see the cardinality of set A is 2. Okay, the
2.
cardinality of set A is 2, but the set A consisting of two elements, that is 1 and 2. Similarly, the cardinality of set B is 3.
Yes, sir.
But the elements of B are different. That is M, S, C. Okay, I am asking about the elements of A cross B. I am not asking about the cardinality of A cross B. Okay. So tell me what are the elements of A cross B?
1
1
comma
comma
math,
Two.
science, 1 C, M,
1 comma M.
1
2
comma
comma
S,
S,
Science.
1
Yeah.
2
comma
comma
C,
C, 2
Yes.
2
comma
comma
M,
2 comma M.
2 comma S,
2 comma
2
C.
comma
2 comma C.
Right. So basically these are the elements, because as you can see this first component, so if you see all the elements, where so you can see in all the elements the first element comes from this set A, okay, and the second component of this all this pair comes from this set B. Okay, so these are the possible elements of A cross B, and as you can see, if the cardinality of set A, if the cardinality of set A is, so here the cardinality of set A
Is
is
2.
2 and the cardinality of set
It
B
is 3.
3. So that's why the cardinality of A cross B is
Is
nothing
6.
but 2 times 3, which is 6. So in general, if I have a set A with m elements, okay, and I have a set P with n elements, this should imply that the cardinality of A cross B is basically the product of their individual cardinality. So this is nothing but cardinality of A times cardinality of B, which
B.
is M n. Okay, so this is how you can define the cardinality as well. Okay, so once you know the set A and B, then you can write down all the elements of A times B, and as well as you can say, even without computing all, without knowing all the elements, you can directly say the cardinality of A times B, that is A Cartesian product B. Okay, so for example, let's say let me just take one more example. Okay, so let's say my set A is 1 comma 2 and my set B is 1. Okay, so what will be the Cartesian product of A cross B?
1, comma 1,
Comma 1,
2,
1,
comma 1,
1,
2,
2,
comma 1.
1.
Correct. And by the same logic, okay, please mute yourself.
Sir, can you move forward? We already know these things.
Okay, so
Hello?
huh.
Excuse me.
No,
Please
sir.
move forward, sir.
Sir,
As
I have doubt
well.
here. Sir, just a second, please.
Sir, you please go on this page because many of us have doubts on this also.
Yeah,
Yes.
so again, let me tell you, there are 2 sessions on week 1 and 2. Okay, so you have enough time. Okay, so
Yes.
don't so I can go fast, and I can finish all the things within this session. But let me go with my speed. Okay. So as you can see, this is coming from this first component is coming from this set, and the second
Yes, sir.
component is
Sir,
coming
when
from this.
have you started this session?
Sorry.
When have you started this session?
I
It's
don't know.
starting time
Okay.
of this session
I don't know
today.
when I started this session. Okay.
I
So
guess it will be better if we don't disturb.
uh, okay. So this is how you define the Cartesian product of any two set. Okay.
I kindly request everybody to please stay muted. There is a
Uh,
lot of disturbance in the class to concentrate.
okay. So once I know the Cartesian product, then basically I can now, so since I have an idea of Cartesian product, now I can move to this relation. Okay, so this is, as you again, like, this is the cardinality of this set is 2, and this cardinality of set B is 1, and that's why the cardinality of A times B is basically 2 times 1, which is 2. Okay, so there is nothing non-trivial in this. Okay, so the next thing is relation.
Sir, excuse me.
Yes,
If A has two sets and two numbers and B have two numbers, then the cardinality will be 4. Then
correct,
the set
correct. Hmm.
then the sets will be like that. For the first one, A comma like that, 1 comma 1 and 2 comma 1. Then if there is a number 3 again, then 1 comma 3 and 2 comma 3 will be the set like that now.
Right, you are saying, suppose my set is, suppose instead of this, suppose my set is A is 1 comma 2 and B is 1 comma 3, right?
Yeah, like
Yeah,
that
yeah. So
only.
then I will get two extra element, that is 1 comma 3 and 2 comma 3. So in
Yes.
this case, the cardinality will be 4.
Okay, fine.
You,
Thank
need-
you
you,
so
need-
much.
you need to consider all the possible product. Okay.
Okay, fine, sir.
Okay, so the next thing is relation. Okay, again, relation is basically completely, once you know the Cartesian product, the relation is basically it comes free with the Cartesian product. If you know Cartesian product properly, then you can easily define relation. So suppose let's say I have two set A, and again I have two set A and B. Okay. So relation, what is relation? Okay, can one of you tell me what is relation?
So relation are the things, are the elements in which are in a set A, and also some of the sets, some of the numbers are also in B.
Sir, mapping of elements from a set to another set is known as a relation.
Yeah, so okay, so again, like, so you are basically giving very vague and in some sense it's a wrong answer. Okay, okay, let me write it. Okay, please mute yourself. Okay, relation. Okay, so just a minute. Uh, Again, like, if you are not going to mute, then basically I will remove you from the session. Okay. Nirmal Kumar, why you are asking to annotate this here? Why? I didn't understand. You are I declined once. Again, you are asking to annotate.
So please go through other topics with relations.
Yeah, yeah. So yeah, so relation is basically it's a relation from A to B. Suppose you have two sets A and B. Relation is nothing but it's a relation is a subset of
The set.
Cartesian product of A times B. Relation is a basically it's nothing but it's a subset of A times B. That's all. Okay. Relation from R to B. Sorry. Relation from A to B. From A to B is nothing but it's a subset of A cross B, right? So for example, suppose if I want to take a relation R, okay, suppose I want to take a relation R from A to B, okay, where my A is nothing but 1, 2 and B is nothing but math, stat, city. Okay, so suppose this. So relation, as I said, relation is nothing but it's a subset of A times B. Okay, so that means if I consider any subset of A times B, then it's basically it's a relation. For example, so if I take R to be this, let's say R to be this 1M and 1S, right? So this is a subset of A times B, right? This is a subset of A times B. Okay, so that means this R is a relation. Okay, similarly, if I consider some different R1, let's say, so what is this? This is 1 times M, 1 times S, 2 times M. Okay, so this is also a subset of A times B, right? This is also a relation. Okay, so one thing is clear, it's not that there is only one unique relation from A to B. We can have multiple relations, right? We can have multiple relations from. Hello.
Can you explain it again?
Please continue class.
Yeah, so basically, so as you can see, we have two different relation on the same set from A to B. Okay, so we have two relation from A to B. So the relation is not unique. Okay, relation is basically it's a subset of A cross B. And similarly, I can define one more relation. Okay, because if it's something like if I take any subset of A cross B, that basically gives me a relation. Okay, if I take, let's say, one more subset, let's say 2M and 1S. Okay, this is also a subset of A times B. This is also a relation. Okay, so we can have lot of relation from a set A to B. Okay, so for a same set A and B, let me finally tell you, for the same set A and B, we can have multiple relation from the set A to B. Okay. Okay, so this is how you define relation. So once we have relation, then we have types of relation. Okay, once we have relation, then we have types of relation. Okay. So again, like so here actually this A and B, they can be anything, right? A and B, they can be any arbitrary set. So in particularly, in some case, it can happen that A is same as B, right? In some case, it can happen that
Just
A
a
is,
second.
yeah.
Sir, here you have taken their two sets in R where 1 comma M and 1 comma 5. That is such that A cross
Which
B.
one? Which one? 5 I have written.
1 comma s. That's 1
That
comma
is 1
s.
comma S.
1 comma S.
Huh.
Then in R1 you have taken 1 comma M, 1 comma S and 2 comma M as a set. Sir, but there are only two sets here.
Sorry?
Sir, but that belongs to in R1 I am talking about 1 comma M, 1 comma S and 2 comma M belongs to A cross B. So sir, there is no such set. 2 comma m, because if 2 comma m is a set, then a new set C will be created.
No, do you agree that R1 is a subset of A times B? Do you agree or not?
Yes, sir, I agree.
So that is the definition of relation, right? It has to be a subset of A cross B.
That doesn't matter that after that other elements also exist there.
It doesn't matter. The only thing it has to satisfy that it has to be a subset of A times B. So you check, you have something, okay? You have something.
Yeah.
If this is a subset of A times B, okay,
Yeah.
then this is a relation from A to B. That's all. Okay, you don't have to check anything else. Okay, if it
Okay,
is a
fine,
subset,
sir.
so the only thing you need to check whether R is a subset of A cross B. Okay, so
Okay,
here
okay.
R is a subset of A cross B. So then R is a relation from A to B. So here
Okay,
R1
okay.
is a subset of A cross B. That means R1 is a relation. That's all. Okay, I don't care anything else. The only thing I need to care whether it's a subset of A cross B or not. Okay, that's
Okay,
all.
okay.
Okay.
And sir, one more thing is there, like that 1 comma m and 1 comma s there is given. But if in R1 if we get m comma 1 and 1 comma s,
So
that
suppose what is your R? Can you tell me? Repeat.
sir, if I have m comma 1 in R1
No, what? Tell me. Yeah, one
in
m comma 1.
m comma 1 and 1 comma s.
1 comma s. So do you think
It's not.
this is a subset of A cross B? Do you think?
No, sir. No, I don't think so, but there are elements too, but same.
No, but again, like you have to go through the definition, right? You have to go through the definition. First, tell me whether this is a subset of A cross B or not.
A cross B. Yes, sir.
This is a subset of A cross B.
Yes.
So this M, if this is a subset of A cross B, right? Then M comma 1 should be a member of A cross B or not? It should be a member of A cross B, right or not?
So, but
Yes.
it isn't a member of A cross B. 1 comma m.
So can you figure it out where M comma 1 is there in A cross B?
No,
No,
sir.
sir, that is 1 comma m.
This is
No,
1
sir,
comma
not
m. So
possible.
1 comma m is not same as m comma 1, right?
Okay.
Yes, sir.
So you have a tuple. So here the order matters, right? So
Okay,
that's why
sir.
this is not a subset. This is not a subset of A cross B. That means this can't be a relation.
Okay, sir. Thank you.
So the only thing you need to check whether it's a subset or not. Okay. So here since you have m comma 1, okay. So that means m comma 1 is not an element of A cross B. Okay.
Okay, sir.
Yeah. Okay. So the next thing is types of relation. Okay. Okay, so the next thing is type of relation. Okay, so so the first thing is identity relation. Okay, so the first one is identity relation.
Sir, just a second. I have a doubt here. At that
Oh,
point of
where?
number of system, number system, their natural number is given as 0, but it starts with 1. So,
No. So for this course, natural number starts with 0. You take it as a definition. Okay.
okay, fine.
Hello.
So,
Yeah.
I have also doubt in the binary set of numbers.
I'll come to that. I'll come to that. Let me stick with this
Sir,
relation.
what is a
Okay, sir.
tuple?
Sorry.
What is a tuple?
Tuple is basically it's a pair. Okay. This is a tuple. Okay. It's a two element. It's a pair of two elements. Okay. So that's why in general you call it as a tuple. Okay.
Okay.
Okay. So identity relation. So so basically, so as basically I said, so sometimes your relation can be from the same set to itself. Okay, so here actually in the general definition of relation, you can define from any arbitrary set to some other arbitrary set. Okay, but for identity relation, we'll stick to only relation that are from a set A to itself. Okay, we'll only talk about relation that are from A to itself. Okay, so here we'll only consider all the relation that are from A to itself. So a relation R, so suppose R is a relation on A. So when I'm saying that R is a relation on A, that means, so you have to understand, so you have to take it like this. R is basically, it's a relation from A to A. So this basically means R is a relation from A to A. Okay, so here both A and B are same. Okay, so suppose R is a relation on A. So when I can say that R is a identity relation? When I can say that R is an identity relation? If it should satisfy this condition, R should be equals to this set A comma A, where A is in A. R should be precisely this set. Okay, if R is precisely this set, then I say that R is a identity relation on A. Okay, it should contain all the diagonal elements. So diagonal elements means all the possible tuples where this first component is same as the second component, and as well as it should contain all the diagonal elements. Okay, that means it should contain A comma A for all A in A. Okay, A comma A for all A in A. Okay, so just give, let me take an example. Okay, so suppose you take a relation R. Okay, R on this set A is 1, 2. Suppose my R is this. Okay, 1 comma 1. Okay, is it a identity relation on A?
No, sir.
No, because as you can see, it should contain A comma A for all A belongs to A. That means it should contain 1 comma 1 and 1 2 comma 2. Right? It should contain 1
No,
comma
sir.
1 and 2 comma 2 and nothing else. Okay, it should not contain anything else apart from these two elements. Okay, so here as you can see, 2 comma 2 is not there. Okay, here 2 comma 2 is missing. 2 comma 2 is missing. Okay, 2 comma 2 is missing. That means R is not an identity relation. Not an identity.
Suppose if the set contains 1 comma 2 or 2 comma 1, that is not identity relation, right?
No. So suppose, let me take this example. R equals to 1 comma 1, 2 comma 2 and 1 comma 2. Is it a identity relation?
No, sir.
No,
No,
sir.
sir.
Correct.
No.
Because as you can see, I have A comma A, I have A 1 comma 1, as well as I have 2 comma 2. But the problem is I have one more extra element. I don't want this kind of elements here. Okay, I don't want this kind of elements. Okay, in identity relation, it should contain all the diagonal elements, and apart from these diagonal elements, it should not contain any other elements. Okay, that is really crucial. Okay, that is actually, in some sense, that is the difference between identity relation and reflexive relation. That I will come just after this. Okay. So as you can see, this is not a identity relation. Okay, so but if I consider this set R, let's
1 1, 2 2, and 3 3.
So identity relation is just repetitive of one element as a pair.
so okay, so your voice is not. Okay, so this is, as you can see, this is a identity relation because it precisely contains all the
Can you repeat it?
diagonal elements. Okay,
Can you repeat it, sir?
Sorry, which part is not clear to you here?
Sir, can we have A having a 1, 2, and 3? Then what should be the
So
R?
3. So if you consider what is your R? Can you tell me?
That should be 1, 1, 2, 2.
Okay. Again, like I'm fed up saying all these things multiple times. Please mute yourself. Whoever is not asking question, please mute yourself.
I have a doubt here.
Audible, sir?
Who is asking the doubt? Can you tell me what?
Devang this side, sir.
I
said.
Sir, here I want to know that, like that, if there are two sets,
No,
one comma
not
one.
Bhavya. Just a minute. I will come to you, Bhavya. Okay. So someone else was asking before you. Okay.
Yes, this is Devang. Actually, I am asking that if A having a 1, 2, 3, then it should supposed to be R is equal to 1, 1, 2, 2, 3, 3. I guess so.
Okay.
Or is it the right or
So
wrong answer?
okay. So again, like you are changing your set A, right? You are changing your set A. 1, 2, 3, right? This is
Yes,
your
sir.
set. So what is your relation on this set A? What is your R?
R should be 1, 1, 2, 2, 3, 3. I guess so.
No, if R is 1, 1, 2, 2, 3, 3, then certainly it's a identity relation. Okay. Because it contains all the diagonal elements. It contains all the diagonal elements, and apart from diagonal elements, it doesn't contain anything else.
Okay.
Right. So this is a identity relation on A. Okay.
Okay, sir. Thank you. Yeah.
Sir, at this point I have doubt. If 1 comma 1, 1 comma 2 comma 2, 3 comma 3 are there, and in extra there are 1 comma 2 and 1 comma 3.
That is what I
Then
explained here, right? That is what I have explained here, right? This is
Sir,
not
I was not
identity,
clear.
not identity relation, right?
Okay.
Because you have a extra element, not a identity relation, right?
Okay,
Because
okay. And sir, and if there are two different sets like 1, 2 and 2, 1,
what do
like
you mean? What do you mean by 1, 2, and 2, 1? So for
1, 2, 1, 2 is an A set, and other A set.
No, you can't. What is your set A? So what is your set A? First tell me.
1, 2.
1, 2. Yeah.
And
What
the other
is
set is 2, 1.
What do you mean by other set? You can't define a relation. See, if you take some other set 2, 1, they are basically the same set, right? AB and ABA are same, right? This is nothing but 1, 2, right?
Yeah.
So they are same set. So how you can say that this is a different set?
No, sir, then it will be considered as an identity relation.
It's the identity.
What if the 3 comma 3 or any one of that element is not present?
Okay, so just a minute. Okay, so again, like you are actually wasting your time. Okay, so the thing is, what basically you can define identity relation from a set to itself. Okay, you can't define from one set to some different set. Identity relation by definition, you define it from a set to itself. Clear or
Okay,
not?
sir.
You
Yes, sir.
can't define a relation. You can't give a identity relation. Okay, you can't give a identity relation from 1 comma 2 to okay
Okay.
2 comma 3. This is not, by definition, this is not allowed, because here A and B are different. Okay, you can
Okay, sir.
only define identity relation when A and B are same.
Okay.
Yeah. Okay, so next thing is reflexive relation. Okay.
Sir, I do have a confusion also.
Oh, where?
Sir, what if all the elements are not present, like 1, 1, 2, 2, and 3, 3 are not present in the.
I have discussed that thing, right?
Yeah.
I have discussed that thing, right? So here I have taken this R, right? Here, if you see 2 comma 2 is not there. So that's why R is not an identity relation, because it doesn't contain all the possible diagonal elements.
Okay, sir.
Yes, can you mute yourself? Yeah, okay. So
Sir,
again,
we can't see your screen.
yeah. So again, let me tell you, please mute yourself. Okay. Yeah.
So can you please repeat the example of identity relation?
Okay. Yeah. Okay, so next thing is reflexive relation. Okay, so again, reflexive relation also you define from a set to itself. Okay, you define reflexive relation from a set to itself. Okay, so reflexive relation you can't define from a set to some other different set. Okay, reflexive relation is always reflexive relation you always define from A to itself. Okay. So, so suppose I have a relation R, okay? Suppose I have a relation R on a set A, okay? So when you say that R is a reflexive relation on the set A, when R contains the identity relation. When R contains the identity relation, that is the only requirement. Okay, that is the only requirement. Okay, if R contains the identity relation, okay, then R is a reflexive relation. That's all. Okay, so you don't need anything else apart from this condition. This
Can you
definition is
repeat it? So,
sorry.
sir, every identity relation is a reflexive relation.
Sorry.
Sir,
Every identity relation is a reflexive relation.
Correct. Yes. Every identity relation is a reflexive relation.
sir, every reflexive relation is identity relation or not?
Every
Reflexive relation
hmm.
is identity relation.
Yes, correct. That is true. Every reflexive relation is a identity relation. Sorry. No. Every
No.
identity relation is a reflexive relation. Okay. Every identity relation, okay. Identity relation is a reflexive relation.
So reflexive relation
Yeah,
is
I'll come to that. Okay, just a minute. But every reflexive relation may not be identity relation. Okay, so I'll come to examples where I will give a reflexive relation which is not identity relation. Okay, so already I have given, just let me repeat the same thing. Okay, let me take this set 1 comma 2, right? 1 comma 2, if I consider this relation, okay, 1 comma 1, 1 comma 2, 2 comma 2, right? So this is a okay, sorry, this is not a yeah, this is a relation. Okay, so because this is certainly it's a subset of A times B. So one thing is it a identity relation?
No, sir.
No, sir. It's not an identity relation, right? But as you can see, identity relation is basically inside R, right? I is a subset of R or not? I is a subset of what is I? I is basically what? 1 comma 1,
1
1
comma 1
comma
and 2 comma 2.
2, right? So I is a subset of R. Okay, since as I said, by definition, R should contains the identity relation. So as you can see, R actually contains the identity relation. Okay, so this part R contains 1 comma 1 and as well as 2 comma 2. Okay, so that's why R is a, so here R is a reflexive relation. Okay, but again, R is a reflexive relation, but it's not an identity relation because you have extra element. Okay, so 1 comma 2, which is not allowed in
That
case of.
means
If it
so
just
that's
contains one
reflexive contains more element.
Sorry.
if it just contains one
Reflexive relation is a subset of identity relation, right?
Identity relation is a subset of reflexive relation. Okay.
Oh, sorry. Yes, sir.
Yeah.
if it contains
So,
only one
okay. So the thing is, what is the difference between reflexive and identity relation? Identity relation should contain all the diagonal elements and it can't contain anything extra. Okay. But in case of reflexive relation, it should contain all the diagonal elements, but it can also contain some other elements as well. Okay. For example, so here R contains all the diagonal elements 1 comma 1, 2 comma 2.
Elements.
Sorry.
Extra elements.
Yeah. So it can contain some extra element as well. So
the diagonal elements are must to have.
yeah. It should contain
Sir,
I,
what is
right?
diagonal elements?
I have already said what is
All
diagonal
diagonal
elements.
elements
Okay.
are necessary. Like all the diagonal elements are necessary. Let us say that the relation you have written above, it only has 1 comma 1 and 1 comma 2, but not 2 comma 2. So is it reflexive or not? As it have one identity,
No.
as it have one
Just
element of that,
what?
but not the whole.
Listen to me. Okay, I got your question. So you are saying suppose R is this, right? Suppose R is this 1 comma 1 and 1 comma 2. Okay. So first of all, whether R contains identity relation?
No, sir.
If R doesn't contain identity relation, then certainly R can't be reflexive. Okay. That means R is not reflexive. Okay. Only thing, don't go for some extra thing. Just stick to the definition. Okay. What is the definition? Stick to that. Okay. And as far as you decide whether it's a reflexive relation, it's asking whether. Just a minute. Let me complete. Okay. So it's asking whether R is a reflexive relation or not. Okay, that is the question. So what is the thing you need to check? You need to check whether R contains identity relation or not. If R contains identity relation, then you are done basically. If R contains identity relation, you can blindly say that this is a reflexive relation. Yeah, please ask your question. Someone was asking something. Yeah.
What if 2 comma 2 is absent on the place?
Sorry.
What if 2 comma 2 is absent on this place?
That is
Means
what I have.
Cartesian.
That is what I have
It will
explained here, right?
be reflexive.
That is what I have explained here, right? Here, basically I have added 2 comma 2, right? I have added 2 comma 2 and here you can see that R actually contains I, right? So that's why R is a reflexive relation.
Sir, if it is only identity relation, meaning 1:1, first set first is 1:1 and again 2:2. So if it is the identity relation, then count it as a reflexive relation or not? Means it contain a different.
Okay, so again, so don't waste your time. I'm not unable to hear whatever you said. Okay.
Please unmute.
I'm unable to hear whatever you said. I'm not able to hear it. Okay. Just a minute.
All of you, please mute yourself. Requesting you.
Speed breakers.
Just give me a minute. Yeah. Okay, so let me take one more example. Let's say my set A is 1, 2, S. Okay, this is my set. So if I consider this relation R, let's say 1, 1, 2, 2, 1, S. Is it a reflexive relation? No,
No,
sir.
sir.
Yes, sir.
Because as you can see, I is not a subset of R, right? I is not a subset of R. What is I? I here is basically identity relation, which is 1, 1, 2, 2, and S,
S,
right?
S.
This is not a identity relation, not
Yeah.
an identity relation. Okay. And if I consider one more relation on this set, okay, so probably this is the last example was I. So 1, 1, 1, 2, 2, 2, 1, S, 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 okay, S, 2. Whether this is a identity, this is a reflexive relation?
Yeah.
Yes, sir.
Yes,
Yes,
it
sir.
is a
It is
reflexive
reflexive
Yes,
relation.
sir.
because it contains all the diagonal elements.
Yes, sir.
Yeah,
Yes,
correct.
sir.
Okay, so let me again go to the symmetry relation. Okay.
Okay.
So symmetry relation, again the same thing. I'll impose the same condition. It's basically, I can talk about symmetry relation when the relation is basically from the same set to itself. Okay, same set to itself. Okay, so symmetry relation doesn't have any meaning for relation from a set to some different set. Okay, it's, I can only talk about symmetry relation from same set to itself. Okay, so symmetry relation, what is the definition of symmetry relation? It says if A comma B, so I can say that a relation is symmetry if A comma B is in R, implies B comma A is in R. That means if A comma B is a member of R, this should imply that if I flip the element, that means if I take B comma A, it should also be a member of R. Okay, so that is so if the relation satisfies this condition, then only I can say that my relation is symmetric. Okay, so again let me take 1, 2, 3. First tell me whether this relation is a symmetry relation.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yeah.
Yes, sir.
So because if I
Sir, this
flip,
will be symmetric relation.
yeah, so whether this is, yeah, certainly this is a symmetry relation. So because what I can do, if I flip this element 1, 1, I'll get basically 1, 1, right, which is in my R. Again, if I flip 2, 2, then I will again get 2, 2, which is also in R. If I flip 3, 3, I will get again 3, 3, which is also in R. Okay, please mute yourself. Okay.
Sir, if there is an 1 comma 3 and if we flip that, then 3 comma 1.
I'll come to that. Okay, just take one more example. Let's say 1, 2, 2, 1, 1, 3, and 1, 2. Okay, please.
भाई चुप हो जाओ साइड में.
Please mute yourself. Whoever is not asking questions, please mute yourself.
Excuse me, sir.
Yeah.
It's look like identity relation. Actually, 1 comma 1, 2 comma 2, 3
No,
comma 3.
I'm now actually I'm not concerned about this identity relation. Okay. I'm asking about symmetry relation.
Is that identity relation?
First three can exist here.
Sir, for the sake of clarity, it would be better if each example is different from the previous one, so that we can understand what would be the difference from the previous. Because I understand that reflexive could be, would always contain identity. So if you give me identity relation as an example of reflexive, I'll get confused. Similarly, when you give me an identity relation as an example of symmetric relation, it doesn't help me much. So if you can give me a unique symmetric relation, which may not be an identity relation,
Yeah,
in
yeah.
that case,
Again, like certainly,
I
see, I
think
started with some
identity relation should
basic.
do only diagonal
Okay,
elements,
so
not other
okay,
elements.
again, like one suggestion, you should again, like you should wait, like you should allow me to complete the thing. So one by one, I will go to some different kind of example. Okay, so I have started with the simpler one. Okay, so again, I will go to some different example. Then I will try to give some different example. Okay, if certainly in a single example, I cannot give you all the possible different example, right? So I have started with just one example. So you should allow me to continue for some times. Then if I didn't cover
First,
your
you
question,
complete that topic, sir. After
then
that,
only
only
you
accept the questions.
ask questions. Okay.
sure,
You
sir. My
complete the topic, sir.
Okay, yeah. Okay, so again, don't try to unmute yourself because you can't unmute yourself. Okay. Let me finish. Okay. Because that is the only option I am left with. Okay, so so as you can see, okay, so it's clear that uh, it's clear that R is not a identity relation. Okay, so if I consider this example, so it's clear that R is not a identity relation because I is not a subset of R. Okay, so R is not a identity relation. Okay, so and since sorry, yeah, so certainly R is not an identity relation, and as well as you can say that R is also not a reflexive relation. Okay, so I is not a subset of R. Okay, so the next thing is what I need to check. I need to check whether R is symmetry or. Okay, so let's go back to the definition. It says the symmetry relation says that if A comma B is in R, this should imply that B comma A in R. Okay, so let me start with each and every element of A. So here 1 comma 2 is in R. Next thing I should check whether 2 comma 1 is in R or not. Okay, as you can see 2 comma 1 is there. Okay, so I'm fine for this element. Okay, so next thing is if I flip 2 comma 1, then I will get 1 comma 2, and it's clear that 1 comma 2 is also in R. Okay, so the next thing is 1 comma 3. If I flip 1 comma 3, then what I am getting 3 comma 1. Okay, as you can see 3 comma 1 is not in R. Okay, 3 comma 1 is not in R. Now I can stop. Okay, I don't have to go and check for 1 comma 2, since there is at least one A comma B for which B comma A is not in R. Okay, so that's why R is not an symmetry relation. Okay, because for 1 comma 3, if I flip, then I am getting 3 comma 1, which is not in R. So that's why R is not a reflexive relation. Okay, sorry, not reflexive. R is not a symmetry relation. Okay, so next thing you take, suppose let's say R is 1 comma 2 for the same set A 1 2 3, 1 comma 2, 2 comma 1, 1 comma 3, and 3 comma 1, and 1 comma 1, 2 comma 2, and 3 comma 3. Okay, so it's now you can see that R actually contains I. Okay, R basically contains I. 1 comma 1, 2 comma 2, 3, 3. Okay. So R contains I. So that means R is a reflexive relation. Okay. Since R contains I, that means R is a reflexive relation. So the next thing I need to check whether R is a symmetry relation or not. Okay. So again, for symmetry relation, I have to check one by one. So if I flip 1, 2, then I will get 2, 1. Again, as I can see, 2, 1 is in R. Okay. If I flip 2, 1, then I am getting 1, 2, which is again in R. Okay. If I flip 1, 3, then I'll get 3, 1. And you can see 3, 1 is in R. And if I flip 3, 1, I'm getting 1, 3, which is in R. And if I flip 1, 1, basically I'll get the same thing. If I flip 2, 2, I'll get the same thing. If I flip 3, 3, I'll get the same thing. That means if I flip all the elements are they are basically inside R. Okay. That means this condition holds for all a comma b in R, b comma a is in also R. That means R is a symmetry relation. Okay. Is there okay? So now, is there any doubt here?
Yes, just one.
Okay.
So they are both symmetric and reflexive, right?
Yes, yes, yes. So R is both symmetry as well as reflexive.
So all three relations are always from A to A only, sir.
Yeah. Whatever this particular type of, so whatever types of relation I'm going to discuss, they are all are basically from A to A. Okay.
Sir,
Hmm.
what is the difference between relation A to A and A to B?
So relation A to A is basically here both your starting point and your ending point, they are same, right? So when you are taking relation from A to A, that means your source and your target, they are basically same, right? That is the difference. When A to A means your source is basically same as, sorry, your target is same as your source. Okay. So in case of A to B, A B can be anything, right? It can be any different sets.
Well, the third example that you gave, is this a equivalence relation or it is just both
I have not
reflexive?
till now I have not discussed about equivalence relation. Let me come to equivalence relation. Okay. Once I discuss transitive relation, then only I can talk about equivalence relation. Okay.
Hello,
Sorry for
sir.
the
What?
interruption. Sir, sorry for the interruption.
Hmm.
Can I ask a doubt in reflexive?
What is your doubt?
Sir, if I'm having a set 1, 2, 3, 4, where I have all the identity sets, one
1,
of
2, 1, 2, 3, 4. That is your A, right?
that is my A,
Hmm.
where my relation has 1, comma 1, 2, comma 2, 3, comma 3, and 4, comma 4.
Hmm.
And there is only 1, comma 3 and 2, comma 4, which is the extra elements.
We have what you have 1, comma
1, comma 4
Hmm.
and 2, comma 3.
Hmm.
These are the only extra elements. So
Hmm.
can I call this relation as reflexive relation?
So first tell me whether identity relation is a subset of this relation.
Yes, identity is completely a subset. There is only
So
2 extra elements.
yeah, so then if identity is a subset, then certainly by definition you can call it as a reflexive relation. Okay.
Okay. Thank
So
you.
can you tell me whether this relation is a symmetry relation or not?
This
Whether
is no,
Not
this is not
symmetric.
No,
symmetric.
sir.
not symmetry, because
Not a
see
symmetry.
if you flip this element, you are getting 4, 1, right?
4, 1
But
and
4,
3, 2.
1,
That is
yeah, again, like I don't have to go to the 2, 3. Okay, because if for a single element, if I flip it, if that new element is not in R, then that is enough for me to tell that the relation is not symmetric. So here you can see that 4, 1 is not in R. That means my relation R is not symmetric. Okay. Okay.
so it is also not necessary that there is 1, comma 2 and 2, comma 4 required to be for reflexive and symmetry.
No. So see, if these two two elements are not here, okay, then R is reflexive.
Yes.
And as well as symmetry also.
It is not mandatory for a symmetric relation to have diagonal elements, right?
It's not mandatory, but if I take if this is my relation, then this is symmetry, right? Okay, it's certainly not mandatory. Okay, but if I remove these two elements, then certainly this R will become a symmetry relation.
Symmetry
So,
also.
but here if I add this element 1, 4 and 2, 3, okay, this
Then
is,
it will be
it is not
identity.
symmetry. It is not
Because
symmetry. Sorry, it is not, yeah, it is not symmetry. If I add these two elements, okay, if I add these two elements, then this relation R is not symmetry, okay. But if I remove these two elements, okay, then this relation will become a symmetry relation. Okay, that is the difference.
Yes. Thank you, sir.
Yeah.
Sir, is it also a identity relation?
You check. I gave you the definition of identity relation.
Yes, it is.
Yes, it is identity, reflexive, and symmetry also.
That it is identity, reflexive, and symmetry.
Yeah, actually,
All.
this, if you take the identity relation, actually identity relation is everything. Okay, identity relation will satisfy all the conditions. Reflexive, symmetry. Again, I will discuss transitive. That will become also a transitive relation as well. Okay, identity relation is a will satisfy all the different
Hello.
conditions. Yeah.
Hello, sir. What if we take three sets A, B, and C, and each have three different elements, and we multiply three of them?
I gave you all the definition, and I have worked out lot of
No,
examples.
no.
You try on your
I
own.
want to conclude that it
Hmm.
is possible we can conclude from three sets it is reflexive or symmetric. If A have three elements, 1, 2, 3, and B have 5, 6, 7, and
No, you try
C
on your
have.
own. Okay.
Please move ahead.
Okay. Uh, so again, like the thing is, sorry, like I don't have all the time to go through each and every doubt. Okay. Okay. So next thing is transitive. Okay. So the thing is, so checking transitive is slightly tricky. Okay, it's not difficult, but checking symmetry, reflexive, they are actually pretty easy. Okay, so you don't have to do much work. Okay, but checking transitive is slightly tricky. It's not difficult. Okay, it's slightly trickier than the previous things that we discussed. Okay, suppose I have a relation. Again, the relation is from A to A. Okay, so this relation R is from A to A. When I can say that this relation R is transitive. So when I can say, so the precise definition is if A comma B is in R and B comma C is in R, this should imply that as you can see, if I have two elements of this form, okay, so as you can see, there is something special about these two elements. So here the second pair, second element of this pair is same as the first element of this pair. Okay, they are same. So if I have two elements of this form, A comma B and B comma C, this should imply that A comma C is in R. Okay. If I have two elements of this form, then this should imply that A comma C is in R. Okay. So that is the condition. I can just a minute. That is the condition for uh, transitive relation. Yeah. So now let me work out a few examples. Okay, let me work out few examples. So so let's say I have a set. So can okay. So is there any okay? Let me mute unmute all of you so that you can ask some specific example which you want me
No,
to take.
so continue with the example, sir. What you can use will last later.
Oh, okay, fine. Yeah. So let's say I have a set A. Let's say my set is let's say A, B, C, D. Okay, so this is my set A, and I have a relation R. Let's say my relation R is what? A, B, B, D, A, B, B, C, C, and D. Okay, this is my relation. Okay, so I want to check whether this relation is a transitive relation or not.
No,
Okay,
sir.
yeah, I'll certainly this is not. But before that, let me slightly try to
Okay.
revise the things that we have already. So as you can see, actually this is not a identity relation, right? Not a identity relation. But one of the good thing is that this is not identity relation, but this contains the identity relation. Okay, so that means R is a reflexive relation. Okay, R is a reflexive relation, and similarly you can check that R is actually not a symmetry relation, because if I flip A comma B, then I will get B comma A, and in this case B comma A is not in R, right? So that means this R is not symmetry. Okay, R is reflexive, but R is not symmetry. Okay. So the next thing, let's go to check whether this is a transitive relation or not. Again, let me try to say it again. So I need to find first. I need to find all the elements which are of this form: A comma B and B comma C. Okay, then if I have elements of this form, then only I need to check whether A comma C is there or not. If I don't have elements of this form, then actually I don't have to check. So it's vacuously a transitive relation. Okay, if I don't have element of this form A comma B and B comma C, then I don't have to check. Okay, these conditions will satisfy automatically, because it's saying that if A comma B and B comma C is there, then I need to check whether A comma C is there or not. If I don't have this kind of elements, then I don't have to check it. Okay, vacuously too. I will give an example where this say one relation will be vacuously a transitive relation. Okay, so before that, let me first
Suppose if A comma D is in the relation here, it's transitive, right?
Yeah. So suppose this is my relation. So let me check whether this relation is a transitive relation or not. Okay. So first we need to find out all the possible elements which are of the form A comma B and B comma C. So this is one element A comma B. So I need to find another element in which the first component is same as the second component of this element. Okay. Okay. I need to find the element uh, where the first component is same as the second component of this element. As you can see in this element, okay, the second component is B. So I have A comma B and B comma D. So then what I need to check whether what I need to
A
check
comma D should be there.
whether A comma D is there or not, right? So whether A comma D is there,
No.
No, sir.
right? So now since this is not correct, so from here itself I can say that R is not transitive. R is not transitive, right? So yeah, so this is not a transitive relation. Okay. Yes. Sorry. Hello. Yeah, what is your doubt?
You may go.
Yeah. Okay, so okay, so let me take one more example. Let me take this set 1, 2, 3. Okay, so and consider this relation R, which is 1, 2, 2, 1, 1, 1. Let's say 1, 3 and 3, 1. Okay. So this is my relation and I need to check whether this is a transitive relation or not. Again, my first task is I need to check I need to check for all possible pairs of this form, this condition should hold. Okay, let me start with the first 1, 2. So I need to, so since now my A comma B is 1, 2, I need to find all the elements which are of this form B comma C. That means the second element, first element of B comma C, that is B, should be same as the second element of my first pair A comma B. Okay, so I need to so here my B is basically 2. So I need to consider all the elements that all the tuples that basically that starts with 2. Okay, so again this is a perfect choice. So as I have 1, 2, I have 2, 1. Okay. So here as you can see 1, 1. So I have 1, 1. So it's clearly 1, 1 is in R, right? And so whether I have any other possible pair that starts with 2, I don't have, because this starts with 1, this starts with 1, and this also this starts with 2. So I don't have any other element that starts with 2. So I can't take uh, uh, any other element in place of 2, 1. Okay, so then I have to move to uh, 2, 1. Okay. So for 2, 1, so here B is 1. So I need to consider all the elements elements such that the first pair of that element is 1. Okay. So as you can see, this is a suitable candidate. Okay, 1, 2. 1, 2. Now, so now we have 2, 2. Okay, but 2, 2 is not in R. Okay, so that means this is not a transitive relation, because 2, 1 is there, 1, 2 is there, but 2, 2 is not there. Okay. Okay, so now let me take an example which is actually a transitive relation. Okay, let's say my R is 1, 1, 1, 2. Yeah, let's say 2, 2. Okay, so this is, let's say this is a relation on the set A equal to 1, 2. Okay, so so as you can see here, let me start with 1, 1. So again, I have to take a element that starts with 1. So here the second component is 1. So if I take, so this is a suitable candidate, as you can see, 1 comma 2, and this is AB, and this is BC. Then if you see AC, which is 1 comma 2, is a element of R. Okay, and so then I don't have any other element that start with 1. Okay, so my checking is done for 1 comma 1. Okay, next let me go to 1 comma 2. So as you can see, I cannot take here 1 comma 1, because here the first element is 1, here the second element is 1. They are not matching, so this is not a suitable candidate. So I have to go to 2 comma 2. Okay, so if I go to 2 comma 2, again as you can see, 1 comma 2 is in R. Okay, and again if I take 2 comma 2, there is no pair here that start with 2. Okay, there is no other pair apart from 2 comma 2. Okay, so if I take 2 comma 2, then what I will have? 2 comma 2, which is also in R. Okay, so as you can see, for all the possible pair that are of the form A comma B and B comma C, A comma C is in R. Okay, so that's why this relation is a transitive relation. Any doubt?
Excuse me, sir.
No,
So this
sir.
2 comma 2.
Continues.
Excuse me, sir.
Can you give the previous example?
Someone asked, someone was trying to asking something. Let him complete. Yeah.
Yes, sir. Sir, this 2 comma 2, the last element there in R. When we are, how is it transitive? I'm not understanding that. Like AB
why
is
it is repeated?
AB should be there, then BC should be there. C should be some.
No, it's saying if
Okay.
If AB is there,
and condition is there, no?
No, and BC is there. Okay.
Yes, sir.
Then SC should be there. Okay. That is the condition. So here AB is what?
AB is 2.
So what is BC? BC is also 2 comma 2.
BC is
right?
also 2 comma 2.
That should imply that AC should be there. So what is AC here? 2 comma 2, right? So that's why this is 2 comma 2 is also there.
So like so if some relation is in this set only, A is 1, 2 and 3. 1, 2, okay. 1, 2. So like 1, 1, like some relation is 1, 1, there is only one element. R is 1, 1. Then this this is going to be transitive only.
Correct. Because see why? Try to go with the definition. You have only one element. You have only one element. So 1 comma 1, right? This is my AB, right?
Yes, sir.
So then what is the possible choice for BC? 1 comma 1.
1 comma 1, yes, sir.
Because here this one, here you have 1, here as well as you have 1, right?
Yeah.
Yes, sir. Yes.
So that means
sir.
then 1 comma 1 is also inner. So that's why this is a transitive relation. And your doubt is not over. Like let me take one more example. Okay. Let me take 1, 2. What about this?
So I think this is also going to be
correct. See, because why? Let me tell why. You have 1, 2, right? This is AB. Okay. But the problem is here, if you see, the problem is I don't have any possible choice for BC, right?
Yes.
Since I don't have any choice for BC, this is transitive. Okay.
So because this AND condition is not going to be fulfilled here.
Yeah, because it's in the condition, if you see, it's saying if. So if A comma B, okay, I guess this is not my definition. Yeah, if you see this, it's saying if A comma B and B comma C is there, then A comma C should be there. It's saying that if I have such type of elements, then only I need to check whether A comma C is there or not.
There or not. Okay, sir.
So here I don't have such type of elements. Okay, then vacuously I don't have to check it. Okay, so this is by vacuously this is transitive.
Thank you, sir.
Got it, sir.
Can you go to the
Sir,
previous?
then it is transitive.
Yeah, that this is transitive. Yeah, yeah, correct.
Okay, sir.
The previous example.
Yeah, previous example. Yeah, this one. Let's say this one, right?
No.
Hmm. Yeah.
So last example.
No, no, no. Someone. So this. Yeah. So I guess.
Just a small clarification in this example 1 comma 1 1 comma 2 and 2 comma 2, just a small clarification, this one is a reflexive and identity function, right? A relation, right?
No, no, no. This is reflexive. But this is not identity.
Okay, yeah, 1 comma 2 doesn't come under identity.
Yeah, yeah.
Okay, thank you.
In this example, we have A comma B, B comma C. Sir, no, sir, this example, not this one.
Who is asking question?
Sir, in the last example that you have given 1 comma 2, where the
Last
R is
example.
1 comma 2. The last example, the downmost example you have written.
I'm not able to. I'm not able to hear you. Okay, that's all. Okay, so
Sir, please explain the last example.
which one? This one, or you are saying this one?
Before this
Sir,
one.
yes, sir, this one, this one.
This one.
Yes,
What
sir.
is your doubt here? I have
Sir,
explained it 2 times.
sir, before both of them.
What is your doubt here?
Sir, before this one.
This one. This one.
Yeah.
This one, sir, correct.
Yeah. What is your doubt here?
Is this 1 comma 2 and 2 comma 1? But A and C are equal.
Sorry. 1 comma.
Take the first two pairs. Here A and C are equal.
Yeah, it doesn't matter. Yeah, that is fine, right?
So we can label them as A comma B and B comma C.
A comma B and B comma C, right? This is of this point. The only thing I need to check whether this is same as this or not. That's all. It doesn't matter whether A and C are equal or A and C are different. Okay, I don't care about that. The only thing I care whether this part is same as this part or not. Okay.
Thank you, sir.
Yeah. Any doubt from here?
Yes, sir. Since the first pair is satisfying, we should check for the second pair. So the second pair is not satisfying, it is not done.
So sorry, can you repeat? I didn't get it. Hallowed or
the first pair we have checked, sir. 1 comma 2 we have checked for
transitivity. Yeah, this is fine.
Okay,
this is fine. But
for the
second
after that we have to go for the second one and
so you
this
have
also
to
should satisfy.
It should satisfy for all possible pairs that are of this point.
Right.
It should satisfy for all the possible pairs. Okay. See, if also it will satisfy for even if I suppose if I include 2 comma 2. Okay. Suppose if I include 2 comma 2 here. Okay. Suppose my relation is this. Now I have added 2 comma 2. Okay. Then it will satisfy for this, right?
Correct.
Then again I have to go forward. Okay. Then I have to start with again. Let's see 2 comma 2. Okay. Whether is there any other possible pair that starts with 1? Let's say 1 comma 2. Then I have 1 comma 1. Okay. If I take 1 comma 1, then what I will get? 2 comma 1, right?
Yes, sir.
2 comma 1 is there. Okay. Just let me complete it. Okay. So then again 2 comma.
One second, sir. Nachket, please mute yourself. Nachket.
Yeah. So basically I'm actually fixing 2 comma 1. Right. My first pair is now I'm fixing my first pair A comma B. So I'm changing this B comma C. Okay. So I have started with 1 comma 2. Then I can see the next choice is 1 comma 1. Please mute yourself. Please mute yourself. 1 comma 1. Okay. So then next suitable candidate is 1 comma 3. Okay. Because here, as you can see, here I have 1 and here also I have 1. So now if I see, then I have 2 comma 3, but 2 comma 3 is not in R, right? That means again, even if I include 2 comma 2, still this relation is not a transitive relation. Okay. Still this
If
relation
we are
is,
comparing 1 comma 2 and 2 comma 1, then we also need to compare 2 comma 1 and 1 comma 2.
sorry?
So if we are comparing 1 comma 2 and 2 comma 1, do we also need to compare 2 comma 1 and 1 comma 2?
Yes, why not? Because for here A, B, so when you are taking A, B and B, C, so here AB is 1 comma 2, right? And BC is 2 comma 1, right? And what you are getting out of this? 1 comma 1, right? And but when you are taking 2 comma 1 and 1 comma 2, what you are getting? 2 comma 2, right? You are getting two different things, right? That's why you need to you need to consider both the things individually. Okay.
Our element will be there to make it transitive, right?
Yeah.
Thank you.
Okay, fine.
So transitive contain extra element or not?
What do you mean by extra element?
Means transitive and extra, some extra elements.
No, what do you mean by what is what you, there is no concept.
Let
So okay, don't mix identity relation and transitive relation. Okay, identity relation you could, so there you can think about some extra element. Okay, here transitive relation, this extra element, the word extra element doesn't make any sense for transitive relation, because in transitive relation you don't have any restriction on the elements. Okay, in identity relation you have restriction. Okay, it should always contain all the diagonal elements, and apart from diagonal elements it can't contain anything. Okay, I'm not saying anything for transitive relation. For transitive relation I'm saying that whatever the set is, I don't care. If this satisfies this condition, my set is transitive relation. That's all.
okay, sir. Okay.
Yeah.
Sir.
Excuse me, sir.
Every
So if we have relation as 1 comma 1 and 2 comma 2, is that a transitive relation or not?
Try to check.
Sir, one last doubt, sir. Can you please go
Hmm.
to the second last example?
Yes, it
In
is
the
a transitive, no,
in this
sir?
example, sir.
This one.
No, the previous one, sir. Not 1 comma 1. The previous one. Sorry. Yeah. In this, if I add another element, like for example, for like 2 comma 1 or something like that.
2 comma.
So like my doubt is like each and every element should we check for transitive, sir? If
Yes,
suppose
yes. You should check for all the possible pairs of this from A comma B and B comma B. All possible pairs. Okay, all the possible pair. Whatever
Okay,
pair
sir.
you can, whatever pairs you can write of this form. Okay, for all this pair you should check whether A comma C.
So like even if one pair is not satisfying, then the whole relation is not transitive, right?
No. If one pair for if the condition doesn't hold for a single pair, okay, it can't be a transitive.
It can't be a transitive. Okay, sir.
Yes.
Understood. Thank you.
Yeah.
Sir, then why the sir? Can you explain the last example?
Okay, so no, sorry, I guess I have spent a lot of time on transitive relation. So let me go to function. So the final thing what I want to say is basically equivalence relation. So equivalence relation is basically, it's a relation which is reflexive, transitive, symmetric. Okay, so equivalence relation is basically, it's a equivalence relation is a relation which is reflexive, symmetry, and transitive. Okay, so since you know all the things, now you can check. So if a relation is symmetry as well as, sorry, if a relation is reflexive as well as symmetry as well as transitive, okay, then this relation is a equivalence relation. Okay.
Just
Okay,
one
someone.
question.
Yeah.
Sir, this also has to be on from A to A only, no? So we have to check for A from set A to set A.
Sorry.
To check whether it is an equivalence relation, we should first verify if it is on set A to set A.
Yeah. Because certainly I can't talk about this reflexive relation, symmetry relation, and transitive relation from set A to some different set, right? So that means it has to be a relation from A to itself. Okay.
Sir, I had one doubt.
Anti-symmetric relation.
What is the definition? Okay, so you want me, basically you want me to revise everything. Okay, so what is an anti-symmetry relation? See, it's basically it's going like a normal session. It's not going like a revision session. Let me tell you. Okay, so the way I'm doing all this thing, it will take some 3-4 sessions just to complete week 1. So it's more or less
Elements
going like a
be
normal session.
repeated in transitive.
Sorry.
Anti-symmetric is if A comma B belongs to R and B comma A belongs to R, then A is equal to B. That is
Yeah. Yes. Just let me quickly go through this anti-symmetry relation. Just let me spend maybe
Sir,
5.
can elements
Sir,
repeat in transitive? Is it an issue?
It is reverse of symmetric ones. I think so.
So
Sir, anti-symmetry is the reverse of the symmetric. I think so.
Yeah, kind of, yeah. So anti-symmetry relation says, what is the definition? It's basically saying if A comma B is in R, right? And B comma A in R, this should imply that A equal to B. Okay. So, okay, so let me start with a simple example. Okay, A is, let's say 1, 2. My relation is what? 1, 2. Okay, this is my relation on 1, 2. So is it an anti-symmetry relation?
Yes, sir.
Yes, sir.
Correct. Because see the problem again, like you have to use the definition. It's saying if A comma B, so let's say A comma B, I have only one element, 1, 2 is in R. Okay. And it's saying if A comma B is in R and B comma A is in R, then only I need to check. If A comma B in R and B comma A in R, then I need to check whether A is equals to B or not. Okay. So here you can see A comma B is in R, but B comma A is not in R. So I don't need to check this condition. Okay, since B comma A is not in R, I don't have to check this condition. So this condition is true vacuously. Okay, because I don't have any elements of this form A comma B as well as B comma A. Okay, so this is a anti-symmetry relation.
So if the elements in transitive relation are repeating, is that an issue?
So just a minute. Let me complete it. I'm talking about anti-symmetry.
Yes.
So now you take 1, 2, 2, 1. Is it an anti-symmetry relation?
No, sir.
No, sir.
There is 1, 1 in there.
So as you can see, 1, 2 is in R, and if I flip it, 2, 1 is in R. But you have a problem here. A is not equal to B. A is 1, B is 2. A is not. So that means this condition is basically it's not true for these two pairs. Okay, so that is not anti-symmetry relation. Yeah, so this is basically more or less the idea of anti-symmetry. You need to check if A comma B is in R and B comma A is in R, then it should imply that A is equals to B. Okay. Yeah.
Okay, sir, I got it.
Yeah, someone was asking something about transitive relation.
So, sir, in the previous question, like elements were repeating. So, is that considerable? Like, is it okay?
Where?
Supposedly, if it is written 1, 2 and 2, 1 2 times, like more than one time, so it is okay?
Sorry, what is your relation?
If it in transitive, it is written 1, 2 and 2, 1. Then it is written 1, 3 and 3, 1. And then it is again written 1, 2 and 2, 1. It is repeating 2, this time. So that is okay.
It's fine, right? Because see, you in a set actually you can repeat. So this set is nothing but it's basically equals to this one. Okay, if you are repeating as a element in a set, basically there is no point that you will count this as a single element. Okay.
Okay.
Right. So this 1 comma 1 is nothing but 1, right? Okay. So if you repeat it also, it's not a problem. You can simply remove the repeating terms. Okay.
Okay.
Yeah. Okay. So
asymmetric relation also we'll discuss. Just one word about asymmetric relation.
Yeah. So yeah, again, like you can check. Okay. So let me start with the functions.
Sir, please move ahead, sir. More topics are left.
Yeah, that I know, but so the thing is, you have to also know, right?
Sir, so anti-symmetric relation is only possible when only one element is given in a set.
No.
Can you give us example for that? Some set where there are other elements present, but also it is also anti-symmetric. I can't seem to write any with the set where.
Try to think of that kind of example. Try to do it on your own. I have given two examples. Okay, this is if you see, probably this example I have defined on on a set with two elements. Okay. Okay, so yeah, so now I guess function. Okay, so functions is basically it's a relation. Okay, so for example, as you can see in relation actually, so for example, if you see this relation, okay, suppose this relation, okay, suppose if you see this relation actually you have 1, you have 2, and you have 3, right? And as you can see here, 1 basically you have 1 comma 2, so that means 1 is going to 2, right? You have 2 comma 1, that means 2 is going to 1, right? And you have 1 comma 3, and 1 is going to 2 and as well as 3, okay, and 3 is going to 1. Okay, so the problem is this kind of thing you can do in relation. Okay, but in case of function you can't do like this. Okay, so for a single element, okay, for a single element, okay, you should have a unique element as the output. Okay, for each element in the domain. So when I'm saying domain, so suppose R is a relation from A to B. Okay, suppose R is a relation from A to B. So that means this A is your domain. Okay, this is your domain. Okay, and this is your codomain. Okay, so when actually you say that a relation is a function, so a relation is a function if each element in your domain, if each element in your domain, okay, they're exactly one element in the codomain. Okay, so as you can see, exactly one element, that means one cannot go to 2 and 3. Okay, this is not allowed. One can only go to 2, and if one is going to 2, then it can't go to any other elements. Okay, so this is basically the difference between relation and function. Okay, in relation, a single element.
Can you repeat once again?
In a relation, a single element can go to two different elements. As you can see here, one is actually going to 2, okay, as well as one is going to 3, but this you can't do it for a function. For each element in the domain, you have a unique, exactly one element in the codomain. You can't have multiple elements in the codomain that is related to 1. Okay, you should have exactly one element in your codomain that is related to a element in your domain. Okay, for let's say.
That means every function can be a relation.
Yeah.
But
By
every
definition.
relation cannot be function.
Yeah, so by definition, actually, you define a function by using relation. Okay, so a function is basically a relation. Okay, suppose you have a function. So function from x to y. Okay, so x is a set and y is basically a relation from x to y. Okay, such that each element of x is associated with exactly one element, that is really important, exactly one element of y. Okay, so so for example, if I consider this function, let's say one relation. So suppose you consider a relation R from set 1, 2 to 3, 4, 5. Okay, so suppose what is my R? Let's say R is 1, 3, 1, 4, 2, 3. So suppose this is a relation. Whether this is a function?
No, sir.
No,
Yes,
because
sir. No, sir.
because one has, as you can see. So if you write it as a arrow, so this is your A, right? 1, 2, and this is your 3, 4, 5. See, if you see, 1 is actually going to 3, and also 1 is going to 4, and 2 is going to 3. But again, this is the problem actually. As you can see, each element of x is associated with exactly one element of y. So here you can see, so 1 is associated to two elements, right? 1 and 3 and 4. That is not allowed. Okay, this is not a relation. Sorry, this is not a function. Okay, now you consider this relation 1, 3. Whether this is a function? Whether this is a function from A to B?
Yes, sir.
Yes.
Why?
It is
Because only
uniquely
one
representing one.
Yeah,
domain.
just write. Let me write it. So you have 1, 2, you have 3, 4, right?
Oh, not a function.
1 is going to 3, right? 1 is associated with exactly one element, right? What about 2?
2 is left over. It's not a function.
2 is not associated with any element, right? But it's saying that every element of x should be associated with exactly one element. So here you can see 2 is not associated to any element. So that's why this is not a function, right? This is a relation, but this is not a function. Okay, so let me take few more examples. I just want to do it properly. Is after. So I guess yeah. So I forgot the set. So A is basically 1, 2, and
B 3, 4, 5.
3, 4, 5. So now if I take this relation 1, 3 and 2, 5. So as you can see, so whether this is a relation, sorry, this is a function.
Yes, sir.
Yes, sir.
It's a function.
Yes, sir. This is a function.
No, one.
Yes, sir. It's representing.
Yes, sir.
It's correct. It's a function.
So as you can see, 1 actually is going to 3, right? And 2 is going to 5. So for each element, basically
Association with
each element in the domain. So each element of the domain is basically associated with exactly one element in the codomain.
Sir, so the codomain can have as many elements as it wants to.
So yeah, you can increase your codomain if you want. Okay, so
I have a doubt regarding this. As you said that elements in the domain cannot have multiple cannot be associated with multiple elements in the codomain. But is the vice versa true? Can an element in codomain be associated with multiple elements in domain?
No, that condition is not required.
Different one.
That condition is not required. For example, let's say that is actually the definition of one function. Okay, so that is the difference between function and one function. So let's say this example. Let's say this one, 1 3 and 2 3. Whether this is a function, whether this is a function.
No, sir.
No,
Why?
sir.
Just check.
Because one is going to 3 and 2 is also going for 3.
But 1 is associated to 3, exactly one element, right?
Okay.
1 is associated to exactly one element, right?
Yes, sir.
2 is also associated to exactly one element.
One element. Okay.
It's not contradicting the definition of function. Okay. So
Okay, sir. Domain.
one cannot go to 3 as well as 4. Okay. But here two elements can go to same element. That is allowed. Okay. Here saying, yeah, you try to read the definition. Here saying
Yes,
each
got
each element
domain,
in the domain.
codomain will not be a problem, but domain must
domain,
be
yeah.
unique. Yes, okay.
Yeah. So this is a function. This is a function. Okay, so again, like so now it's more or less the idea. Okay, so let me jump into some of the things. Okay, so now can you tell me, so the thing is, what is here? So what is the codomain? So if you see, what is the codomain? Codomain is basically what? It's basically set of all possible output of the function, right? So codomain is what? Codomain is basically set of
possible output.
All possible outputs. So, but one more thing, one more terminology is there, that is range. Okay, that you have to understand. So range is what? Range actually range is a subset of codomain. Okay. Range
of outputs.
Yeah, correct. So range is actually, it's a subset of codomain, but there is a slightly difference between range and codomain. The codomain is actually set of all possible outputs. Range is what? Set of all actual output. Okay, set of all actual output. Okay. So for example, if I take this function, what are the actual output for this function? What are the actual output for this function?
3 and 5.
3 and 5.
3 and 5. Okay. So for this function, let me denote this function as f. Okay. Suppose this is my function.
3.
So function, so f of 1 is 3. If I write it using some algebraic symbol, then f of 1 equal to 3, f of 2 equal to 5, right? So if you see, actually 3 is the output, 5 is the output. So 3 and 5, these are actually actual output of this function. So this is a range. This is the range of this function. Whereas the codomain is what? 3, 4, 5 is the codomain. Okay, 3, 4, 5 is the codomain. Right. So this is the difference between domain and codomain and range. Okay. Range is basically the actual output. So codomain is basically the set of all possible.
Set of possible outputs.
And what about this? So this is also a function, right? This is also a function. So what is the range of this function? Sorry, what is the codomain of this function?
3, 4, 5.
3, 4, and 5.
3, 4, and 5. So what is the range of this function?
3.
3.
This is 3. As you can see, range is a subset. It can be also a proper subset, right? It can be a proper subset as well. Okay, this can be a proper subset of range, can be a proper subset of codomain. Okay, here also range is a proper subset of codomain. Okay, so again, so now actually I was more or less I was giving some toy example. Okay, let me go back to let me do a sudden jump and let me go to some advanced thing. Okay, so because this is more or less very easy to do. Okay, so now let me take this example. Okay, so I'll use sort of algebraic expression to write the thing. So as you can see, this is a function from where to where?
R to R.
So what is the domain here?
R.
R.
Real numbers.
R.
This is
R
Real
will be
numbers.
domain, sir.
And what is the codomain here?
All real
R.
numbers. F.
R.
F will be.
This is codomain, right? And
Yes, sir.
how I define this function? My function is basically x goes to x square. Please mute yourself.
Please unmute all.
So this is my function, right? So if I write it in, so if I try to write it using my relation thing, then basically what it will look like, this is basically x comma x square, right? Because it's taking x to x square. So if I go back to my previous thing, then this is my a, this is my b, right? And x actually varies over all the reals. So if I write this as a relation, so this is basically, I can write it like this, x comma x square, where x is basically in R. Okay, so this will contain huge number of elements. More precisely, it will contain infinitely many elements. So for example, if I take 1, then I'll get 1. If I'll take 0, 5, then it will probably take 0 0.25, 0 0.5 square. And if I take 3, then it will give me 9. Okay, so this contains lot of elements. Okay, which certainly I can't write. Okay, I can't write all the elements of this this set. Okay, this is basically, let's say, as since this is a function from R to R. In particular, this is a relation from R to R. That means it should be a subset of R cross R. Okay, so this is a subset of R cross R. Okay, but I don't know whether this is equals to a R cross R or not. That I don't know, because the only thing I know, this is a subset of R, and that is what I need. Okay. So this is a function from R to R. Can one of you tell me what will be the range of this function?
0 to infinity.
X square.
The set of positive numbers.
0 to infinity will be range, sir.
So x square, as you can see, the square of a number is always positive. Okay, the square of a number is always positive. So the range is what? 0 to infinity. So can you tell me the bracket?
Natural numbers?
Yes, sir. First
All
is a square and
How come natural numbers will be the range? How come natural number? So if I take
Integers.
if I take
Positive integers, sir. 0.
1 by 2, if I take 1 by 2, then what will be my output?
1 by 4.
1 by 4. 1 by 4 is a natural number?
No.
No, sir.
Then why natural number will be a range?
Positive integers should be the range.
I think all the square natural numbers.
Rational numbers.
All positive integers.
All
Real numbers.
Real number.
Real numbers.
So the range is basically what? The range of this function. The range of this function is 0 closed interval to infinity. Because if I take 0, then basically I will get 0. Okay, so 0 will come in the range. Okay, so it's the range of this function is 0 comma infinity. Okay.
Why not
So
infinity and
excuse
closed
me, sir.
interval?
Just now you have taken the example of 1 by 2, right? Stating it when it is squared, it will become 1 by 4. Then that 1 by 4 doesn't fall in this range, right?
Why? 1 by 4 doesn't fall in this range. Why?
All the real numbers are the codomain, so
It
why
falls
not?
in this range.
Okay.
1 by 4 is a positive real number, right?
Okay.
So here I'm taking all non-negative real numbers, right? This is basically all non-negative
Okay.
real numbers.
Got it. Understood.
1/4 is non-negative. So 1/4 is there. Yeah.
Yes, understood. In between 0 and 1.
Yeah. So, so that's why this is the range of this function. Okay.
So what is the codomain in this? Same, 0 to infinity, isn't it?
No, this is range. The codomain is R.
Ah, okay.
X square.
Sir, in the next session, can you take but I have a doubt in some squared error.
Yeah.
What I said?
Yeah. Let me complete. I'll try to complete this function and types of function. Okay. Just give me some time. I'll take.
Yes, sir. This is the most bothering topic.
So at least I will try to complete week 1. So I don't think I can go to week 2. Okay. So
sir, for week 2, will there be a separate session?
no, not separate. Actually, there was 2 sessions for week 1 and 2. So you can ask there. So this is the range of this function. Okay. So now let me take this example. Okay. R to R. Okay. So let's say x is going to x. Right? What will be the range of this function?
All real numbers.
All the real numbers.
Correct. All the real.
Range will be same as codomain. All the real numbers.
All the real.
And codomain will be the same.
Yes.
Range
So this is my codomain. This is my domain. And if I compute the range, then range is basically all the real numbers. Okay. Because if I take pi as my input, then I will get pi. If I take 2, my input, I will get 2. Okay. If I get 3.14, my input, I'll get 3.14. So all the reals are actually the range. So here range and codomain, they are same. Okay. So next example, let's say take
This one. This one function.
Sorry.
This one function.
Can't hear you.
Okay, sir.
Let's say natural number to natural number, and where this, let's say n goes to n plus 1, right?
Yes.
So what will be what is the domain here?
All natural numbers.
All natural. What is the codomain? What is the codomain?
Natural numbers.
All
natural numbers. All natural numbers.
Now you tell me what will be the range of this function?
1 to infinity.
1 to
infinity.
Correct. 1 to infinity. So if you see, so this domain is basically from 0, 1, 2 up to infinity. So if I take 0, then I will get 1. If I take 1, I'll get 2. If I put 2, I'll get 3. If I take 3, I'll get 4. Okay, so on. So I'll get all the numbers which are greater than equal to. So this is my output, right? So this is my input and these are my output. Okay, so I'm getting 1, 2, 3, 4, so on. So the range of this function is basically what? 1, 2, 3, 4, infinity. So on. Okay. So now let me tell you one more definition. So suppose you have a function, okay, from A to B. So when you say that this function is surjective or onto, okay, this function is surjective or onto, they are basically the same thing, they represent the same thing. If range of the function, okay, range of the function is same as the codomain of the function. Okay, the range of the function is same as codomain of the function, which is basically, sorry, codomain of the function. So here the codomain is basically B. If the range of the function is same as the codomain of the function, then you say that my function is onto. So whether this function is onto, whether this function is onto.
No, sir.
No.
Why?
No, sir. Because codomain also includes 0. It does not
Correct.
include.
Correct. So my this is my range set. This is my range set. And what is my codomain set? My codomain set is 0, 0, 1, 2, and so on. And as you can see, you have 0 here, but you don't have 0 here. Okay. So that means range is not same as codomain. So that's why this function is not on. Not on. Right? This is not an onto function. What about, let's go back and check whether this is a onto function.
Yes, sir. Yes, sir.
Because as you see, my range is all the reals, right? All real numbers I am getting as my range. So here range is R, and this is also same as the codomain. So this is a onto function. What about this one?
Not onto.
Why? Why?
Because all real numbers do not include only 0 to infinity.
So what is my range here? What is the range?
0 to infinity.
0 to infinity.
0 to infinity. So question is whether
Codomain is R. So
the question is whether this is equals to R? No, right?
no.
Because minus 1 is here, but minus 1 is not here, right? So this is not a onto function. Right? This is not a onto function. Okay, so let me take one more example. I'll slightly change. I'll take the same thing, but I'll slightly. So my function is from 0 to infinity, right? And what is my function? X goes to modulus of x, right? So what is the domain here?
All real numbers.
All real numbers. All real numbers. All positive real numbers.
What is the domain?
Domain is all real numbers. It might be negative
All real
also.
numbers.
What is
It
the
can be negative.
All
codomain?
positive real numbers.
All positive real numbers.
Not all positive, actually.
All real numbers.
No. Codomain is, so don't say actually. I know you know you know the codomain, but you are saying it wrongly. So it's actually not all positive real numbers. Actually, see, 0 is not positive. Okay. So the proper way of saying this, actually all non-negative. All non-negative real numbers. Okay. So we are actually excluding all the negative numbers. Okay. So we are excluding all the negative numbers. So that's why this 0 closed, infinity open is actually all non-negative real numbers. If I write this 0 comma infinity, then you can say that this is basically all positive real numbers, because I am excluding 0 here. Okay. So there is slightly difference in the terminology. Okay. So this is my domain and this is my codomain. So now you tell me what will be the range.
Same as codomain. 0 to infinity.
All non-negative
All
again.
non-negative real numbers.
Correct. So the range is basically 0 to infinity. Okay. Because you will get, because you have a modulus sign here. So always you will get positive or maybe say 0. Okay. Because if you take 0 here, then you will take 0. And if you don't take 0, then always you will get some positive thing. Okay. So all the outputs are basically all the actual outputs is precisely this set. Okay. 0 to infinity. So this is same as the codomain. So
this is onto function.
Yeah. Correct. Okay. So yeah. So let's say one more example. Let's say you have a map. Let's say from I'll take one more example, but before that, let me take this one. Okay. So n is n by 2 if n is even, and n goes to 0 if n is odd. Okay, what is the domain of this function?
Natural numbers.
All natural numbers.
This is domain, this is codomain, right? So what about the range? What about the range?
Infinity.
What do you mean by 0 to infinity?
Rational numbers.
How come rational number can come? Because see, range is a subset of codomain, right? Range is a subset of codomain. So here codomain is n.
It is also
All
natural numbers,
even
sir.
numbers, sir. All positive even numbers is the range.
Yeah.
Is there any other answer? Someone said all positive even numbers. Is there any other answer?
All
Zero,
positive real
zero,
numbers.
Zero is also included.
zero and all positive.
Someone said all positive real number. Okay, so I'm not getting angry. So try to think. Okay, so
Non-negative even numbers.
yeah, this is possible. Like someone said non-negative even numbers. That is, I don't know whether this is correct or incorrect, but this is a acceptable answer. Okay, because your range should be a subset of your codomain. So that means range should be a subset of natural. So someone saying real number, positive real numbers. How come a positive real numbers can be a subset of n? You should not say this. Okay, this certainly this can't be possible. At least you should your guess, whatever is your guess, it should be a subset of natural numbers.
The range is natural numbers.
Yeah, that is the correct answer. But
non-negative natural numbers.
okay, someone said rational number. It's not possible because rational number is not a subset of n. Okay.
Non-negative even numbers, I told.
Yeah, even number you told. Okay, so that is okay. That is certainly as I said.
Natural even numbers.
That is again like that certainly can be answer, but certainly R can't be a possible answer. Okay, but let me try. Okay, so what will be the image of 0? What is the image of 0?
0.
0 is 0. So 0 by 2 is 0. What is the image of 1?
0.
0.
Yeah.
0. 1 is odd, right? If
Yes,
n
yes.
is odd, the image of the element is 0. What is the image of 2?
1.
1.
What is the image of 3?
0.
0.
What is the image of 4?
2.
2.
0, right?
And 0. 6.
3. If you take 8, you will get 4.
4.
If you take 10, you will get 5. Right?
Yes.
Now can you see what will be the image?
All natural numbers.
All
Correct.
natural
All
numbers.
natural numbers.
Yeah. So basically what actually you are doing, if you want 16, then you take 32. 32 will go to 16, right? If you want 20, you take 40. 40 will go to 20. Okay. So as you can see, all the natural numbers will actually come into the range. Okay. So
Codomain and range are same.
correct. So
Then is it
So
a onto
this is
function?
surjective and onto function.
yeah, that is the definition of onto function, right? So why you are asking? So I said, right, if the range is equals to codomain, then it's onto. So here range is same as codomain. Okay, so this is a onto function. Okay, so is there any question you want me to discuss? Some specific question about ontoness? Because I don't want to discuss anything.
What
So
about into function?
yeah, I'll come to that. I'm asking about not into, actually it's one function. Okay, into is not.
Bijective and injective.
Yes, this is surjective, right? This is a
Yes, yes.
surjective. So I'll come to one
Terms
function, but
injective and bijective also.
yeah, that I will come.
Okay.
So let me, what actually I'm asking, if some specific example, see, I actually gave, I discussed few example that basically came to in my mind. Okay, so if you have some specific example you want me to discuss, then just let me know. Okay, so I can discuss anything specific example. Otherwise, I will move to one or injective function.
If f of x is x square plus 5, it is not onto, isn't it?
From where to where? So from where to?
Plus 5.
No, that is your function, but what is your domain? What is your codomain? If you don't know domain and codomain, how you will decide whether this function is on to or not? First, mention the domain. What is the domain?
Domain and codomain are natural numbers.
Natural
numbers.
Right?
And
so this is your function, right? So first tell me, if you take 1, what you will get?
6.
6, right?
Yeah.
And if you take 2, what you will get?
9.
9. If you take 3, you will get 14, right?
Oh, I got it now. Yeah.
Then you will get 19, right?
Okay. Yeah. This range is not same as codomain.
So as you can see, this is your codomain, right? And certainly you are missing lot of elements from the codomain, right? So that's why this is not onto function.
Okay.
Onto or surjective, whatever you like. Okay, so fine.
Thank you.
Okay, so let me move to injective function. Okay. So, please mute yourself. Please mute yourself. So the next thing, so basically I have discussed surjective function. So next thing is injective, or you can use some different word, that is one. Okay. So what is the thing actually that you can do for a general function and that you can't do for injective functions, that you need to understand. So initially I said that if I take 1 2, okay, this is my function, let's say 3 4 5, 1 goes to 2, 2 goes to 3. This is a function, right or not?
It is a function.
This is a function. Yeah, so this is a function, and the problem is this is a function, but this is not an injective function. Not a injective function. Let me tell you why. Not an injective function. Because as you can see, this kind of thing is not allowed. Because here, someone actually said whether the reverse is applicable or not. So for injective function, the reverse is also not applicable. So as you can see, 1 is going to 3, 2 is also going to 3. This is not allowed. Two different elements. See, 1 and 2, they are two different things, right? In the domain. In the domain, 1 and 2, they are different things. But they are going to the same thing in the codomain, right? They are going into the same thing in the codomain. That means f of 1 is 3 as well as f of 2 is a 3. This is not allowed. Okay. So for injective function, image of all the element, okay, or image of two different element should be different, right? Image of two different element should be different. But in this case, image of two different element, they are same. Got it? The definition is clear?
Sir, if you can just come again.
Yes, sir.
Sorry?
Sir, if you can just repeat it again.
Yeah, so basically what I'm saying, if you consider, so this is a function. So as you can see, 1 is going to 3 and as well as 2 is going to 3. But the problem here is, what is the problem? So in my domain, 1 and 2, they are completely two different elements, right? 1 and 2, they are completely different elements, but they are actually going to the same thing. Okay, they are going to the same thing. This is not allowed because in the definition of injective function says that if I have two different element in my domain, okay, if I have two different element in my domain, the image should be different. Okay, then only I can say that my function is injective. Okay, I'll come to some general thing, but before that, let me try to draw some few this diagram, and from there itself let me tell you. Okay, so this is, let's say, 1 2 3, and let's say this is A B C. 1 goes to 1, 2 goes to 3, 3 goes to C. So whether this is a so first tell me what is the range of this function.
ABC.
Range is equal to
1, 2, 3 is right, sir.
Range is ABC.
ABC is the
B and
range.
C.
ABC, yeah.
Range is ABC, right?
And codomain also.
Yeah, so this is a surjective function. Right?
Surjective.
This is a surjective function. Okay. So this is surjective or onto. What about injective? Whether this is a injective function?
Yes,
Yes,
it
it
is
is.
injective
Yes,
also.
sir.
It is also injective function.
So as you can see,
Yes,
if I pick any two elements, their images are different, right? If I pick 1 and 2, they are actually going to some different element, right? 1 is going to A, 2 is going to B, and similarly any two arbitrary element. If I also pick 2 and 3, they are also going to different element. Okay, if I pick let's say 1 and 3, they are also going to two different element. Any two different element, they are going to two different element. That means this is injective. Okay. So
As range and codomain are equal, we can call it surjective also, no, sir?
yeah, this is a surjective function as well as this is from.
And every injective will be a surjective
No,
also.
no. I'll come to that. Just give me a minute. So
Okay.
let's say 1, 2, 3. Now let's say 4, 5, 6, 7. Right? So this is, let's say, 1 goes to 4, 2 goes to 7, 3 goes to 5. What is the range of this function?
4, 5, 7.
4,
4, 5,
4,
7.
5, and 7.
Is it a surjective function?
No.
no,
No.
sir.
No.
No,
Right?
sir.
No. So
Because
this
code
is not a surjective function. What about injectiveness?
Yes, it is an
Yes, it is
injective.
Yes,
injective.
sir. It's an
This is
objective
injective,
function.
right? This
four
is
different.
This
Three
is injective because 1 is going to 4, 2 is going to 7, 3 is going to 5. So
Yes, 1 to 1. It is going 1 to 1.
this is injective, right?
Yes.
Yes, sir.
Yes.
So this is surjective but not injective. Sorry, my bad. This is injective,
Injective but not surjective.
not surjective. Okay. So let me I'll give you few more examples, but let me go back and see the question that we have already discussed. So my question is whether this is an injective function.
Yes. Yes.
Yes.
This is injective. It's clear, right?
Yes.
1 is going to
That
C,
is an
2
injective function.
going to 3.
Yes, sir.
So if you take any element, it will go to some other element than
Big number.
the previous one, right?
Yes, sir.
So
Yes.
for different element A and B, so in other words, what basically I am saying, for different element A and B, the image are different, right?
Different.
So this is injective, right?
Yes.
But this is not surjective, right?
Not surjective, yeah.
Not subjective.
This is
It's
not
not
subjective.
subjective
Yeah, we have
because
discussed.
the domain is all natural numbers.
Yeah. Not domain. The codomain is all.
Yeah,
all the
codomain is natural numbers.
Yeah. So again, let's come back to this example. Okay, let's come back to this example. Whether this is injective?
No, sir.
This is not. This is clearly not injective, right? Because if you see, I have 0, 1, 2, and so on. And also I have 0, 1, 2, so on. And you see now, what is the image of 0? It's 0, right? 0
Yes,
is
sir.
going to 0.
0.
What is the image of 1? It's going to
0.
as well 0. So you have two different
It is
elements
not in
which is going to the same thing, right?
same. Not one or more.
So that means it's not a
Injective.
Injective
function.
injective function, right? This is not, but this is a surjective one, right?
Surjective.
Not
Range
So
a,
if a function is not injective, it has to be surjective, right?
I never said that. I never said that.
rule, no?
not at all.
Maybe or it might not be.
Yes, sir.
So as you can see, right, here the function is injective but not surjective, right? Here the function is not injective but surjective, right?
Yes, sir.
So it's kind of, they are completely independent of each other. Some function can be surjective but not injective. Some function can be injective but not surjective. Okay.
Completely depend on properties.
And some function can't be both.
Might be neither
Surjective
subjective
as
Yeah.
well
nor
as
So
injective.
so they can't. Yeah. Neither they can be surjective nor they can be injective. Okay. Maybe I'll probably I'll give some. Maybe we'll
Yeah, we
see.
have an example, sir, if you go
Yeah.
up.
Yeah.
1, 2,
So
only for 3 we have given.
yeah. So what about this one? Whether this is injective?
No, I think not.
No, not injective.
Not
Because
injective, right?
when
Because
Not injective.
so
99% is
if you see the if I take -1, what is the image of -1?
1 plus 1.
What is the image of 1?
1.
1.
It's still 1.
So basically, if you see, I have -1, I
They
have
are both.
1, but they are going to 1, right?
Yes.
So this is not allowed. So this again, this function is surjective but not injective, right?
Yes.
Yes, sir.
Similarly, what about this one? This one?
This is injective.
This is injective, right?
Injective, yes, sir.
This is injective.
This is
That is
injective, but
injective.
yeah, but not surjective. Okay.
Not sir.
Uh, what about this one? What about this one? Now you tell me, what about this one?
This is not injective.
It's not injective.
Not injective, sir.
This is
It's injective, sir.
most importantly, this is not injective and also
Not surjective.
Not surjective.
That's not surjective.
this is not injective, this is not surjective. So okay, let me now take some
Okay.
surjective we have already discussed, right?
Yeah, okay. Yeah.
We have already discussed, right? What because the range is basically 0 to infinity, right? Range is
If a function is not surjective or is not injective, then it means it is not a function only, right?
no. Why?
Here the codomain is
because-
also infinity, is it?
Just one question at a time.
Yeah, got it.
Just one question at a time. Yeah. So
this is 1 to 1, no, sir.
this is
X is related. It should be 1 to 1, no, sir.
no. Why this should be 1 to 1?
Not 1 to 1, not 1 to both are not.
Because see, what is the image of -2 here?
All right.
What is the image of -2 here?
-2 is 4.
What is the image of 2 here?
Still 4.
So then you have
It's not
-2.
1 to 1.
You have 2. Both are going to 4, right?
Right.
Yes,
Is it allowed for a for 1 to 1 function?
No, sir.
No, sir.
So then this is not
Injective.
Right.
okay. So let me slightly. So now you have some basic idea about 1, 1 and 1, 2 function. Let me slightly increase the level of difficulty. Let me take R to R and X goes to X minus 1 times X minus 2. Now try to don't try to answer about the surjectivity, because for surjectivity you need some to tell about to easily tell about this function is not surjective. You need some concept of this. If you know parabola, then probably you can easily tell. Okay, but I don't want to go. But for the time being, just let's stick to the injectiveness of this function, whether this function is injective or not.
Yeah, it is.
Not injective, sir.
Not injective.
Who is
It is
sharing? Who is
Sir, it's
sharing?
Sir, I'm
yeah,
unable to see the screen, sir.
Who is? Yes, Anurag.
yes, Anurag.
Why you are sharing your screen? Yeah. So what about you can see my screen, right?
Yes, sir, we
Yes,
are.
sir.
No, this is not injective. Yeah.
Not injective.
So why this is not injective?
Sir, because if we put 1 and 2, we will get answer as 0.
Yeah. So basically, the answer basically lies in this thing. Okay. So if you see, if I put one, what I will get?
0.
0, right? And
Yes, sir.
similarly, if I put 2, then what I will get?
Then also it is 0.
0.
0, right?
Same number for both.
So it is
So,
not one.
so then this is not injective, right?
Yes, sir.
It's not injective.
Not injective. Okay. So again, to actually to tell more about the surjectivity of this function, actually you need some concept that is not coming in maths. Sorry, in week 1. Okay, because it's basically, if you see, this is a parabola, right? Correct.
Yeah.
Have you studied? Okay, parabola is there in this syllabus.
Yes, sir.
So
Yes, it is a quadratic, it becomes a
So it is a
quadratic equation.
quadratic equation.
So actually, if you see, yeah. So this is third week, right? So this is a quadratic equation, right?
Yes, sir.
So that means actually, what will be the range of this function? This is basically all the points which are here.
Above them.
So these are the points, right? So that means you are missing a lot of points which are below. So these points actually you are missing. Okay, these are not in your range. Okay, only this part, this red part is in your range. So that means this is not.
Range and codomain are not equal.
So this is not surjective. Okay. Okay. So anything else? Let me check some.
I have one doubt, sir.
What is your doubt? Tell.
Actually, domain is n, natural numbers, and codomain is also n. The function x equal to x square minus 5. Is this
Just
a function or not?
Just a minute. Let me write.
Okay.
Tell me, what is your function?
N to n, domain and codomain, n to n. Actually, x to x square minus 5. Is this a function or not, sir?
X square minus
5.
5, right? So
is this a function?
So first tell me, if I put 0, right? 0 is in your domain, right?
Yes, sir.
So if I put 0, what I am getting?
I'm getting minus 5.
So minus. So what about minus 5? Minus 5 is in your code. Minus 5 is in your codomain or not?
It's not a natural number.
No, not a
So that means this is not a function, because
yeah, sure. Yeah, okay.
by
Okay,
definition the image should be inside codomain, right?
Okay, sir. Okay, thank you very much.
Okay, anything else you want me to discuss? Because I don't think I'll go to
The question is from R to R, the same question.
Yeah, R to R, this is a function.
If it is R to R, it is
a
N to R is also same. No?
Yeah, it is surjective.
R to yeah, even if you take n to r, that is also a function. If you take a natural number, you will certainly get a real number. If you change from r to r also, this is a function. Okay, but certainly n to n, this is not a function. Even if you take z to z, okay, this is a function.
Function, sir.
Okay.
This is okay. So if okay, what about okay? Since you have asked, even if you consider from z to z, is it an injective function?
Yeah. No.
Yeah, if you no, you see, you have a square term here, right? See,
Yeah, it is not
once
injective.
once you have a square term, you should be very careful. Okay, when you have a square term, you should always try to check. You should able to check it easily that this is not a most likely it should not be injective function, right? Because see, when you have a square, you have an advantage because minus 1 will go to minus 1 and 1, they will go to the same thing, right? If I take minus 1, what I will get? Minus 4. Minus 4, right?
Minus
If I take 1, then also I'll get minus 4.
minus 4.
So then this can't be injective. Okay. So
But it is a surjective function.
what about surjectivity?
Same domain and codomain and range will be.
Yes, sir.
Codomain and range will be same. Yeah.
Yeah.
Sure.
So it is surjective.
Try to check.
No, sir, it's
Sir,
not a
it was
No, sir, it
surjective.
is not
No, sir,
subjective
it's
also.
Not onto.
Right?
Because
no, sir, it's
Try
not
to
because range and codomain is not equal.
see the image of minus 1 and 1, they will go to the same thing, right? Minus 2 and 2, they will also go to the same thing. Minus 3 and 3, they will also go to the same thing, right? So where minus 1 and 1 will go? Minus 1 and 1 will
Minus
go to minus 4.
4.
What about minus 2 and minus? So again, 0 will go to uh, minus 5.
Minus 5.
So minus 2 and 2 will go to what?
Minus 3.
Minus 3.
Minus 1. Minus 1, sorry.
Oh, sorry, minus. Yeah,
Minus 1.
minus. Then 3 will go to 4, right?
Yes, sir.
Then you will get minus 4.
4 will go to 11, I think.
16, yeah, 11.
Yes.
So
11.
so
11.
so this is your range set, right?
Yes.
Yes, sir.
It's not equal to codomain.
Codomain is all
the real numbers.
real numbers.
Yeah.
So we can check this
Integers.
by using the vertex formula.
Sorry?
So the vertex of the parabola, if we put the vertex parabola on this equation x square minus 5, we get minus 5 to infinity. So it's not
Minus 5.
No, that is yeah. So that is one way to saying that you should not get whole integers. Okay, but again, like you don't have to go to parabola. It's pretty easy to check. See, when you have very simple thing, try to so when you have square, so most likely it will be not injective. So you try to provide some few examples. Okay, you try to write down few numbers and check what are the images. Okay, so whatever we have done here, we didn't do anything magically. We have wrote down all the things and we have checked. You try to check. Okay.
So if you have a cube, sir, if you have a cube term, then we should check for one to one also.
Yeah. So for example,
Sir, just please pardon why natural numbers cannot be injective. N to N.
Which one?
So the first example, N to N, natural numbers.
This one, right?
Yeah, yes.
This is from n to n. This is not a function itself. Okay. If I have a function only, then only I can talk about the injectiveness and surjectiveness of this function. If that relation is not a function, then I don't have to go there and check. So
Sir, why it is not a function? N to N?
you take from n to n, right? So when I'm writing this n to n, right? What is the meaning of this thing? That means all the image of all the elements should land inside n, right or not?
Yes, sir. Yes.
But if I take 0, what I will get? If I take 0, I'll get -5, right?
How, sir?
This is your formula, right? X goes to x square minus 5. So
Okay, okay.
if you take 0, what you will get? -5, right?
Okay, okay.
So but actually you are landing somewhere outside of your codomain. Okay.
Okay.
So when you are taking a function, the image should always be inside your codomain. It can't
Okay.
go beyond your.
Got it,
That's
sir. Thank you. Got it. Thank you.
okay. Someone asking Q. Okay. So the thing is, yeah. Let's say n to n. Let's take x goes to x cube. So I'll do it for n. Maybe I'll go to r. So what about this function? What is the image of 0? 0, right? Image of 1 is 1. Image of 2 is 8. Image of 3 is 27. So on. So whether this function is injective?
Yes, sir.
Yes, sir.
Yes, sir. And it's clear that this function is not surjective, right?
Yes, sir. It is not surjective.
Not surjective, right? Not injective, but not surjective. But there's something magic will happen if I consider the same function from R to R. Okay. Let's say my function is from R to R. Okay, x goes to x cube. Okay, what about this function?
Take -1.
Injective, sir.
Not injective. Why?
Because minus value is
Yeah.
-1 tends to -1.
So with the minus
Please
also same
mute
and
yourself.
positive values
Okay.
also will get same.
What is the
Not
image
same,
of
negative value.
No, sir. The function is injective.
Injective. It is
Injective, sir.
what is the image of -1?
It's injective.
Minus one.
-1.
What is the image of 1?
It's
1.
So again, this will not work, right? No, why this is injective? Tell me why this is injective.
So
The domain goes for a single codomain.
not
Sorry?
injective.
One
For
on one.
every value of x, there is only one value of.
Yeah, why? You tell me why. I'm saying why. Tell me why.
Because it is cube.
So
Correct.
because the sign value.
Yeah, because see,
Always.
the thing is, what? If A is not equal to B, right? If A is not equal to B, that means A cube is also not equal to B cube, right? Correct.
Yes.
This statement is true or not?
True.
Yes, sir.
So that means
Yes,
in other words, actually what I am saying, if I have two inputs, two different inputs, the output are also different, right?
Yes, sir.
So that's why this is injective. This is injective, right? What about, it's clear or not why this function is injective?
Yeah.
It's one on one, different.
Yeah. So what about surjectiveness?
It is surjective.
Yeah. See, because see, if I take 3 power 1 by 3 in my domain, what I will get? 3, right?
Yes, sir.
3. Yes, sir.
If I take minus pi power 1 by 3, see, minus pi power 1 by 3 is a real number, right?
Pi.
I will get
Pi.
Minus pi.
minus pi. Okay. If I take pi power 1 by 3, then I will get pi. So to be more to be more specific, I can get all the real numbers in my output, right?
Yes,
I can
sir.
get whatever real number I want. If I want 10, then what I should take? If I take 10 power on 1 by 3, then I will get 10 as my output. Okay, so I can get all the possible outputs. Okay, so that's why this function is surjective.
Surjective.
So this is injective as well as surjective.
Subjective.
So there is a special name for the function which are both injective and surjective. So that you call bijective function. When a function is
Surjective as well as objective.
both injective and surjective, you call this function as a bijective function. Okay, there is a special name for this. There is nothing.
Pardon me, sir. Can you just repeat this topic, bijective?
I'm not saying anything. I have not said anything. Like so I basically what I said that if a function is both injective and surjective, then that function is bijective. Okay. So for example, I have given this question. So here actually this function is both surjective as well as injective. So that's why this function is bijective function. Okay. So for example, this is not a bijective function because this is injective but not surjective. This is not bijective function. Okay. Again, if I consider z to z, this is not bijective because this is not injective as well as not surjective. Okay. So yeah. So finding.
Thank you, sir.
Yeah. So, but again, like if you take this example, actually, this is actually this identity function from R, let's say R to R. If I take this function, x goes to x, this is actually injective as well as surjective. So this is a bijective function. Okay, this is the example of a bijective function. Okay, so yeah. So is there any other doubt you want me to discuss?
Sir, can we check?
So we have not gone through the Venn diagrams and union and intersection.
See, the thing is, okay, so it's not possible for me to discuss each and everything from week one. Okay, so that you can get only in the normal session.
So
But
we
this
will
is a
start week 2 today.
sorry.
So we do
Week
some
2
week
also will
2 today.
Yeah. I'll tell to the next person. He will actually discuss week two. Okay, don't worry about it. So in the next section, so there are basically 4 sessions. Okay, so in the next session, that is basically it's more of a doubt clearing session. So I'll tell him to discuss the concept of week 2. Okay, don't worry about it. Okay,
Sir,
but before that, ask, do you have any doubt from question you want me to discuss related to this concept?
Sir, for a bijective function, can we say that number of element in domain, codomain, and range have same number?
Yes, correct. Because you have a one-to-one correspondence, right? Each element. So
yes,
what do you mean by bijective? So bijective will somehow look like this, right? When you have A, B, C, and when you have 1, 2, 3, and A is going to B, let's say B is going to 3, C is going to 2, right? This is a bijective function. So that means the element are same. So if I change, add some one element 4, this is not a bijective function, right?
No, yes.
So that's why if I have bijective function, that means the cardinality are same. Okay.
Cardinality of same. Okay, sir. Thank you, sir.
So there was a question in week 1 graded assignment, question number 10. It's
What is it?
related to the relations. If you can discuss that question.
What is that question?
You want me to repeat? You want me to tell you the question?
Yes.
A survey was conducted on pollution of 525 ponds
Have you checked the
across India.
solution of that question?
Yes, sir. I have checked that, but I couldn't understand the solution. If you could just discuss the second part of that question, the question number 10.
Is it that long question? That very long question you're asking?
Yes, sir, with that
That
Venn
is the
diagram.
set.
The question
That
number
is
10 is
set.
just regarding if it's reflexive, transitive, symmetric, or equivalence.
No. As far as I remember, there is a question that you need to do.
It is an
Probably.
interlinked question.
Okay. Yeah. That is got it. Okay. So this is, I guess, this is not that difficult. Okay. Yeah. Tell me this question. Question number 10, right?
Yeah, question number 10 of
So
graded assignment 1.
yeah. So basically, it's saying define a relation on the set of 22 ponds such that 2 ponds are related if both are polluted by
Fertilizers and pharmaceutical products.
fertilizer and pharmaceutical products, right?
Yes, sir.
So first tell me whether this this relation is reflexive.
Yes, sir, it is.
This relation is reflexive. No, this can't be reflexive.
Please.
No, sir.
Just uh, let me. So so you are so what is your A? First tell me. So here what is your A? So you are defining a relation R on a set A, right? What is your set A?
It's 525 pounds.
It's basically all the 525 bonds, right? And how you defining this relation? A comma B is in R if what? What is the condition?
If both are polluted by fertilizer and pharmaceutical products.
Yeah, so if both are polluted by F and P, right? This is the condition, right? Hello, am I audible?
Yes, sir. Yes, sir. You're audible.
So my question is whether all the ponds are polluted by F and P. Whether all the ponds are
No, sir.
so
No,
there
sir.
are so there are few ponds that are not polluted by F and P, correct or no? So
Yes, sir.
for
Yes.
these ponds A and A can't be inside R, right? Correct or no?
Yeah. Yes. Yes, sir. Correct.
Because if A is not polluted by F and P, then certainly A and A can't be inside R, right? So that means R is not what?
Not reflexive.
Reflexive.
Not reflex. What about symmetry?
Symmetric. It is symmetric.
It is a symmetry, sir,
You have
because
A comma B. Suppose A comma B is in R, right? If A and B are polluted by F and P, okay, then B and A are also polluted by F and P, right?
Yes.
That means B comma A is also in R, right? Next, uh, next what you have? Transitive, right? So transitive means what? So if A comma B is in R and B comma C is in R. So if A comma B is in R and B comma C is in R, that basically means that
A comma C also.
AB is polluted by F and P and BC is also polluted by F and P. Okay. So in particular, A and C are also polluted by F and P. Correct or not?
Yes, sir.
That means A comma C is in R. So this is transitive. Okay. Got it?
Yes, sir.
Yeah.
Yes, sir.
Okay. Is there any other doubt?
So why it is not reflexive, sir?
I said, right, you have some ponds that are not polluted by F and P. Okay, if you have a pond, let's say M, if this is not polluted by F and P, then certainly M and M can't be inside R, right? Because by the definition of relation, A comma B is in R if and only if A and B are both polluted by F and P. But you have still few ponds that are not polluted by F and P, but by some other products. So these ponds can't be inside your relation. That means this is not a reflex.
Hello.
Yeah.
Excuse me, sir. This is 1.5 activity 1, act 1. I don't get the answer. That's why I'm. Suppose Sheetal birthday is on the Pth of the October and Karthik's birthday is on the Qth of November, where P and Q are perfect squares. If Sheetal was born a day before 10 days,
What is
then the value of P
one
minus 2Q.
what
1 day.
is 1.5? 1.5, right?
Yes, sir.
1.5 question number?
Question number only 1.5, sir. 1-1. Activity 1-1. No?
Okay.
Question number 5, sir.
Yeah. So suppose the Seetal's birthday is on the 5th of October. Okay. And Karthik birthday is on Q of November, where P and Q are perfect square. Right?
Yes.
And if Seetal born 10 days before Karthik, then what will be the value of P minus
PQ.
PQ? Okay, so you have a lot of information. So Seetal born on 5th of
October.
Seetal born on 5th of October, right?
Yes, sir.
And you have Karthik.
Yes.
So he was born on Q of
November.
Okay. So the thing is, P is a perfect square, Q is a perfect square.
Yes.
Right? And the difference between their birthday is basically 10 days. Right?
Right.
So what are the perfect square in the month of October?
25, 16.
1 is a perfect square, right? 1 square, right? 4. 2 square is a perfect square. 3 square is a perfect square.
9, 16, 25.
No, you can't take 6 square, because if you
16.
take, yeah, correct. So you can't go beyond 25, right? Because if you take 6 square, then you will get some
36. So
yeah,
36 won't be there.
yeah.
Sir, if we take 25th October and 4th November.
Sorry?
Sir, if you take 25th October and 4th November.
Again, see, that is the problem. Again, I'm saying, wait, okay. So you are basically giving me the answer. Then you solve it. Let me go step by step, right?
Yes. Okay.
So these are the possible dates in which Seetal. So these are the possible birthday of Seetal, right? Because
Right.
it's saying. So similarly, what are the possible birthday for?
Same, sir. 1 square, 2 square, 3 square, 4 square, and 5 square.
Yeah. And you have one more thing that is given, right? The difference between their birthday is 10 days, right?
Yes.
Now,
Yes.
can you figure it out?
P minus Q is equal to 10.
Yeah. So basically, the difference between, if you see, the difference between Seetal was basically born 10 days before Karthik, right? So
Right.
if Seetal was born on 25th of October,
Okay.
and suppose Karthik was born on 1st of November.
Okay.
Is it possible that Seetal was born on 25th of October and Karthik was born on 1st of November? Is it possible?
No, sir. No.
Because
There is no 10 days between.
Yeah. So now you try to figure it out, that what are the possible dates that you can take, so that it will give you some 10 days. Probably this one and this one will be.
Oh.
Right? Yeah, most likely, or probably either it will these two things will give, or probably these two things will give.
Oh.
So 25th October and 4th November.
Sorry?
25th October.
Yeah, you compute. Okay, it's not a big deal. You can compute that.
So I have a question on activity number 1.6, question number 5.
So this part is clear, right? Whoever asked this question, now it's clear,
Yeah.
right?
Yes, sir.
Yeah.
Thank you very much.
Sorry?
Activity 1.6, question number 5.
Question number 2 also, sir, in activity 1.6.
Question number 5.
Yes.
What is your doubt in question number 5?
Sir, how do I approach this one? Not understanding this question.
Okay, I'll do one option. Okay, I'll do only one option. Okay, you have to do according. So for to help me. Okay, so first tell me what is the option number 1?
So the option number 1 is 0 to 2.3.
0 to 2.3, right?
Yes, sir.
0 is open or closed?
Open, sir.
0 open. 2.3 is open or closed?
Closed.
Okay, then union?
Union 2.3 to 3. 2.3, 3.
2.3, comma 3. Open
Yes,
and
sir.
closed. The left.
2.3 is open and 3 is closed.
3 is closed. Okay, this is probably in one bracket, right?
Yes, sir. And intersection 0 to 2.3. Both are open.
0 to 2.3, right?
Yes.
So this is a set A. Okay, this is a set A. This is a set B, right? You need to find all the points which are common to these two sets, right?
Yes, sir.
So first tell me, what is this set A? What is this set A? So basically what you are taking, so you have a number line, right?
Yes, sir.
You have a number line. This is your number line. So this is your 0, right?
Yes,
0 not included, because 0
yes.
you have open bracket. Then you are going to 2 by 3, 2.3. Okay. And again you are going to, so this set is basically 2.3 to 3, right?
Yes,
then what will be the union of these two sets? What will be the union of these two sets? So for the first set, you are taking 0 to 2 by 3.
2.3.
Sorry, 2.3, where 2.3 is included. For the second set, you are not including 2.3. So you are excluding 2.3 from, then you are going up to 3.
Yes.
So what will be the union of these two sets?
0 to 3.
0 to 3.
0 to
0.
3.
So 0 will come in open, right? Because we are not considering 0. Okay.
Yes, sir.
And then you are intersecting this set with 0 to 2.3. So now you have 0. Please mute yourself. 0, 3, and you have another set 0 to 2.3. Right? Now what are the elements that are common to these two sets?
2.3 and 3 is 0.
Sorry?
0, 3 and 2.3.
One set is basically all the real numbers from 0 to 3. Another set is all the let him answer. Okay, just a minute, let him answer. So another set is from 0 to 2.3. What are the elements that are common to both the sets?
0 to 2.3.
Right, because if I take a element from this set after 2.3, that is not common to both the sets, right?
Yes, sir.
Because this is that maybe say 2.4, this is in this set, but this is not in this set, right?
Yes.
So the intersection is what? 0 to
2.3.
What will be the bracket for 2.3?
Closed.
Why closed?
So because we are taking 0.3.
No, so in this set, if you see, we are not considering 2.3.
Yes, sir, we are
2.3
not
so for this set, actually we are not considering 2.3. Okay.
Yes, sir.
So that means what we should get here?
Open bracket.
Yeah. Got it?
Yes, sir.
Yeah, you can try similarly for the rest of the 4 options.
Okay.
So one doubt, sir. So can we represent this using the Venn diagram for this union?
No. How you can?
Not possible.
No, you can represent, but okay, again, like this is basically the same thing. I am actually, instead of drawing like this, okay, drawing like this, I am basically drawing some line. Okay, that's all.
Sir, I have doubt, sir.
Hmm.
What is the difference between proper subset and subset?
Proper subset is a subset, okay?
Yes.
So when A is a proper subset, so when I can say A is a proper subset of B, okay, if A is a subset of B, but A is not equals to B. Okay. For example, if I take A to be 1, okay, and B to be 1 and 3. As you can see, A is a subset of B, right? But A is not equals to B.
Yes.
That is the difference between subset and proper subsets.
Okay, sir. Thank you. Thank you, sir.
Yeah. Okay, then I'll mostly I'll stop the session now. Okay. And I'll tell that maybe probably Piyush will take, so I'll tell him to discuss the concept of week 2 as well.
Just
Yes,
one
sir.
more thing.
Week 2 is left, so please arrange for a week 2 session.
Yeah, definitely. Yeah.
Hello?
Yeah.
So can you please provide the slides?
See, I can
It's
provide,
very
but
compact for the revision.
do you think this is useful?
Yes,
So
sir.
actually, it's very compact for the revision. That's why I'm asking.
No, this will be available in the YouTube.
No, I
The
certainly.
slides is very compact. That's the reason.
No. So I certainly I'll upload. I'll inform them to upload the slide, but I don't think it will be much useful because see, you can understand, you can go through it if you watch the session. Okay, because I have not see these are very I have written very badly in some sense. Okay, nothing is precise. Okay, so but again I'll upload it. Okay, don't worry about it. If you want, I can put it in portal. Okay.
Thank you, sir.
Yeah. Okay then. Yeah.
Thank you,
Thank you,
sir.
sir.
Thank you.
Thank you, sir.
Thank you, sir. Good
Thank you,
night,
sir.
guys.
Thank you very much,
Thanks.
sir.
Thank you. Good
Arrange
night.
for the week 2 session also.
Yeah. So don't worry about that one. And it's definitely it's going to happen. Okay. So don't worry
Okay,
about
thank
it.
you, sir.
Yeah.
Thank you. Thank you.
Mm.
Thank you so much, sir, for your
Thank you,
patience.
sir.
Thanks.
Thank you, sir.
Bye, sir.
Thank you. Yeah. Bye. Good night. Yeah.
Good night, sir.
Good night.
Good night, sir. Thank you, sir.